Okay. Good afternoon. I just checked the leaderboard page for assignment 1, and most of you already well underway, but seems to be a quite challenging task. Keep trying, and I expect that there is a group that can pass my score. All the previous years, some groups managed to do that, so I'm hopeful to see that this year as well. That being said, you don't need to hurry up because you can plan accordingly. But today, given the time, we will start introducing the chapters on deep learning, which also means that next week you will be given the second assignment as well, which will be a computer vision task using any sort of deep learning model that you want to use on a, again, large set of image examples. So that's coming up next week. So for today, what remains, apart from this introduction, let's say, to deep learning, depending on how far that we get, we also have the last chapter left to finish in the supervised essentials, and that's moving away from those fundamental techniques, from evaluation, from interpretability, and finally start basically introducing the key techniques that in daily life, if you ever are confronted with tabular data, that you will utilize going forward, which is basically bagging and boosting based techniques using tree ensembles, as well as some, let's say, as an introduction also to the deep learning part, some techniques that have tried to bring transformer-inspired architectures from the deep learning world to the tabular setting as well. And that's what we'll also discuss later on today. Now, as always, a bit of news. It's going quite rapidly. I have highlighted some articles, but there's more underneath it to say. For instance, OpenAI has introduced GPT 5.4, and as always, there is like a fantastic slide that highlights how well that they're doing in terms of benchmarks. That being said, things are a bit rocky in the US government at the moment in terms of them having embraced, or the Department of Defense having embraced OpenAI to be their AI provider. The CEO of Anthropic, so Cloud, going wild on that as well. And also OpenAI currently being boycotted by a large amount of users that are moving away from this because of that reason and their involvement with the US government. Now, I have few opinions about politics in general. I focus more on the technical side, and I also know from previous years that whenever there is a boycott like this, it's easy to say that you boycott something, but to actually execute it, maybe not. But that being said, Anthropic has seen an influx of new users over the past days as well. So yeah, it seems like all the large AI labs in the world currently are having trouble at the moment, so OpenAI being one of them. What also plays a role in this is that at NVIDIA's side, things are not going that well either. NVIDIA CEO Jensen Huang has said that apparently the last investment round that they put in was their last investment round, literally, that they're not planned to supply any longer OpenAI and these other large AI players with investment funds, also because there is more and more critique being raised in terms of, well, where these investments actually go towards. There's a famous meme going on that if NVIDIA invests in OpenAI and OpenAI invests in Oracle data centers and Oracle invests in NVIDIA because they need to buy GPUs, that at some point the rug disappears, let's say, or the curtain disappears, and people will be left wondering what remains or what the actual return on investment is there. So given the current situation also, that's all to say, are we close to an AI bubble? Financially speaking, maybe so. So I think the months going forward might be relatively interesting to follow up on. Like I said, on the other side, Anthropic is apparently struggling to cope with an exodus from ChatGPT, which is good news for them. It's always nice that you have to cope with too many users rather than too little users, right? So this is basically also highlighting that boycott group between 1.5 to 2.5 million users that are running away from OpenAI and are switching to other alternatives. What I find surprising, or when I read this article, is that apparently they're running away from one centralized player to another one. We have had some other news coming from Anthropic as well. Their head of research, I believe, resigning, and again, them playing around with starting up a model welfare team because they're more and more afraid that models are getting quote-unquote conscious. To which extent that is actually marketing, of course, needs to be discussed and asked. But yeah, seems like the fight is still going on. Maybe not so much on the technical side anymore, but on other aspects nowadays. And then, yeah, this is in line with that. So, yeah, Trump can't help himself once he has made a choice. Apparently, he sticks with it. So, same for OpenAI. So, Anthropic is on the way to be banned from US government. Officials have a couple of weeks to kick out every usage of everything not OpenAI related, apparently. So, yeah, weird things are happening on the US side and on the US players. And if that was not enough, apparently it's the same thing on the Chinese side as well. Maybe a bit less apparent for us, but also there. What we saw in the recent weeks, and I think it was even in the news a couple of weeks ago, that Qwen, Alibaba's model line, had been releasing a new family of models under Qwen 3.5, which a lot of people meanwhile have said are extremely good, especially for an open weights model, and that there are a lot of interesting tricks being applied there, interesting solutions being applied there, that makes this family of models very strong as a local option, let's say, if you do not want to use one of these centralized parties and you just would like to run something locally on your beefy computer or whatever. But also there, things are not going very well. Because apparently, and again, for Western news sources, it's a little bit harder to figure out, but there has been some messages being posted on WeChat and a lot of that going on. Apparently, at first, Alibaba was not even that much aware of what this team had been doing and how good that their model or model family line actually was. So they brought in additional people there, as it typically goes. So the finance guys jump in, the HR people jump in, the marketeers jump in. And apparently, this is all due to one specific person, Lin Junyang, who was the head of the Qwen developments at Alibaba, and out of the blue suddenly decided to resign, being followed by a lot of his fellow team members who followed suit and also resigned there. And currently, people are wondering, is Qwen 3.5 the last open weight, half open source good model that we will see there? What's going to happen there? So seems like everybody's having trouble in terms of the large players in this large LLM context. Now, in terms of some good news, there is also some news coming, at least from Microsoft. You wouldn't believe it, given how involved that they still are with OpenAI. But they have an internal team as well. They have done so for a while. And although it's not in line with things such as what Gemini is doing these days with Nano Banana version 2, or with the Gemma line of models, which is another very small set of models which is capable to do a good reasoning job. But also Microsoft for a couple of years now has been working on models specifically focused on reasoning on images, which is basically you give it an image prompt, as you see here, for instance, together with a textual prompt. And then basically the model integrates reasoning aspects in terms of being able to either analyze the image, describe the image, caption the image. So there are the typical tasks that are being benchmarked here. Perhaps provide some even near real-time descriptions of an image, which is especially important for people who are maybe vision impaired, for instance. If you look at how these models can play a role to give benefits to those kinds of users. It's still an interesting kind of set of models to work on. And the main interesting part, again, does not come in the fact that this is the best reasoning model out there. So they call this Phi internally, so we're already at version 4. But the fact that they're able to squeeze this in a very smallish amount of parameters. 15 billion, that's something that, given some optimizations, given some quantization that you can run on a smartphone or a laptop these days. There are others that do this as well. Like I said, Google has Gemma but which hasn't been updated for a while now. There is a model called Moondream that does something very similar, which is also quite still state of art these days. So yeah, this goes to show that you can utilize a large language model like a Nano Banana or Gemini 3 or GPT 5.4 to do all of these things as well, but there is still a keen interest to kind of squeeze this kind of capability or image understanding at least capability in the smallest amount of parameters possible. Also, it's open weight. Also means that this is something that you can install locally using Ollama and you can utilize on your local machines. And again, in the realm of assignment number 2, it might be interesting to see or have a comparison between the more traditional deep learning approaches where you basically take your standard efficient net convnet and you throw that on the problem, rather than maybe using models like these and utilizing these as well as classifiers. They're good enough that you can, instead of asking them to write a caption for your travel blog, that you can ask them, hey, I need you to classify this image into the following 10 classes. Please just give me one response and utilize that as your model, basically. No training involved, no fine-tuning involved, just out of the box utilizing it. So we'll come back to this or these series of models in what will follow later on. What we also, or as a final slide here, I have something called Obliteratus from a person called Pliny the Great, as it goes nowadays, but who has been working for a couple of years on trying to jailbreak models. Jailbreaking means, as you would normally do with a device, like you get root access or you want to install anything that you want. Same context, jailbreaking for LLM means they normally refuse to give certain answers. If you would ask a question like how to make a bomb, for instance, or how to make drugs, they refuse that. And that's typically because these models have been heavily, after their pre-training and instruct fine-tuning steps, they have been trained or they have been reinforced through human feedback in order to make sure that they refuse to give answers that might be a little bit related to tricky aspects. And what this is basically a library that implements a lot of very novel approaches which do not, or which are all geared towards making sure that you can obliterate, which is what this is called, obliteration of models, that you can obliterate a given large language model, given that you have access to the weights, and basically uncensor it. And that's fun, of course. If you utilize this, you can then utilize this model that you have obliterated to ask it how to make a bomb or how to make drugs if you want to follow in the footsteps of Walter White, let's say, or you want to ask it some tricky geopolitical questions. But what's mainly interesting is the line of techniques that are being applied here, because this all focuses on things that we used to do in general fine-tuning of models, and mainly this comes from the image model domain, things such as LoRa, low rank adaptation, and are now being applied in the setting of language models as well. And what the general idea is, you don't want to train or take these 20 billion parameters that you have and completely fine-tune them again once more in order to uncensor a model. You want to be able to run this on commodity hardware on a general consumer CPU and make the minimal amount of changes in the least amount of time to be able to basically play with the weights that you have there. So there is a lot of research interest, like I said, for multiple reasons, but the kind of understanding or the deeper understanding in terms of how you can take a trained model and then change it afterwards is also very interesting to see here, right? So that's something also maybe to play around during the weekend, but I found this also pretty cool as well. Okay, so back to supervised essentials. So like I said, we have been through our series of favorite models, starting from our standard logistic regression, moving towards decision trees, moving towards KNNs. And all of those introduced a backbone of well, important aspects in terms of that. From the one hand, we started very statistically with very few coefficients, but where we already saw that there is like a loss function involved. And then later on, when we talk about deep learning, that's what we'll pick up on. on the KNN side, we saw that this was purely data-driven, like given a good distance metric, you can do a lot with just a very simple model, which is still something that we utilize nowadays if you talk about retrieval, augmented generation, and vector lookup and things like that. And on the decision tree aspect there, we saw that, okay, a single decision tree is understandable. It's not perfect, it has a tendency to overfit, but that forms the backbone for still a lot of the modern supervised techniques that we utilize today. That make one key change, and the one key change will be that we will not now train a single decision tree, but we will train about 300 of them and mix them together. So that's what we'll talk about today. So we'll talk about three ensembles. Ensemble in French means together, so multiple models acting together, working together. So that's one large aspect. And then we'll also introduce a couple of tabular deep learning techniques as an introduction to the actual deep learning chapter that will follow next. So we'll talk about bagging and boosting, the two main forms of how you can put models together in some sort of ensemble, right? And what's the basic motivation here? Well, from a general perspective, you can wonder, before we have introduced a couple of learning techniques, a couple of supervised algorithms, there are way more out there as well. And you might be trying to check a couple of those on the data set that you have at hand, and maybe some of them do better than others. But you might at some point ask the question, well, if I would have some way to combine multiple models together and stick them in an overall pipeline, would that make sense? Would that work better than just using any of those models in isolation? And indeed, there are many reasons why you might think that that makes sense. And perhaps the first reason is that you might notice that maybe some of your models have more trouble to make good predictions on one subsegment of your data set at hand. They have trouble at making predictions for maybe a younger group of customers in your data set, versus other models that have less trouble there, but maybe then have trouble on other subsegments. So apparently the intrinsic workings of how these algorithms work, they might cause them to do well or worse on particular still kind of structures in your data set, let's say, or patterns in your data set that they are not able then to fully inherently exploit, but you can still somehow notice them during your evaluation. And if that happens, then you will notice, well, if I would have a way then to combine their strengths at least, right, and not combine their weaknesses, then it seems that this combination of such models might make sense, right? And the primary goal then, why you would want to do so, is because you're not happy with the actual accuracy or area under the curve of one particular model, but you hope to increase the accuracy of the combination of models. And of course, we are very often interested in accuracy, so that seems like a very key idea, like, can I push it even a little bit higher? Can I bring my accuracy up even a little bit higher? But there are other reasons as well, like so to increase performance is obviously a primary reason why you might want to do so. But there is another and perhaps even more important reason, given that we go far enough in terms of complexity, as we will see. But another important reason why it might make sense, or why it will make sense to combine models with one another, is to make them more robust. And we will see that there are ways, maybe strangely so in the beginning, but there are ways that will lead you to a setting where the combination of a lot of models is actually a more robust combination than just a singular model. And by robust, we mean always robust in terms of generalization. So less prone to overfitting on that test set that you have, or less prone to overfitting later on. And again, such a combination of models is called an ensemble. And there is always like the, well, in terms of accuracy at least, an easy anecdote that you can, or a metaphor that you can utilize. If I put a jar filled with jelly beans on the table here, and I would just ask a single person in the room, how many jelly beans do you think that there are in this jar? Probably your estimate will be quite off, right? It's not easy to just at a glance see how many candy pieces are in this, this jar. But if I would take the estimate of multiple people and I average them together, I will see that I will get closer and closer to the actual answer. That's something that has been tested in real life, and we will see kind of a similar effect going on with the combinations of models as well. And that also reveals that you already get kind of both outcomes. Both your actual answer becomes better, so your performance increases, but your distribution also becomes more robust overall. So the question here is, can we have it all? We saw the issue of overfitting, where we make a model too specific or too complex, like a decision tree that we trained all the way down. So we didn't use early stopping or we didn't use pruning. We saw the exact aspect of, well, my training data I can fit perfectly, but at some point this thing is getting more and more wordless on unseen data. And if you take the decision boundaries also in terms of at a glance, inspection of robustness, again in the simple two-dimensional case, but you can see that the decision boundaries here, they're basically, they manage to capture some patterns, but they also have a lot of noise in there as well, right? They're very noisy, they're very extreme in some places. Essentially what I would like is to keep the main patterns there, still keep my accuracy high, but to smooth out this decision boundary somewhat. So yeah, before we said you have that model and then you just apply early stopping or pruning. You use a strong validation setup. So you end up somewhere at this red line, your decision boundaries do become smooth, but you might still not be happy with the overall accuracy then that you reach, right? You might still say, well, okay, fine, at least now the gap between train and test accuracy or loss, whatever, error, is lowered, but I'm still overall not very happy with the accuracy that I end up with. So do I have a way where I can still push a model which kind of scales in terms of complexity further to reach a higher performance level, but without this horrible cost of overfit? And that's exactly what ensemble techniques will help us with. And as another maybe simpler idea, which is less commonly approached nowadays, but another kind of easy method to, as an example, is to say, well, let's say that you would like to stick to linear classifiers and your data set for the most part looks linearly separable, as is the case here, except that there is this weird odd group of red cases as well over there in the circle. Well, if I would be able to have another linear boundary in there and combine linear classifiers to construct a more complicated or complex, not complicated, but complex classifier, might also be an interesting idea where I can still use a backbone of very simple models, but at least combine them together into something that becomes stronger. So what could we do? Sorry. We can think first of very simple combination approaches, which are quite trivial. In real life, this is rarely what you will utilize, although sometimes it still is utilized, but just to illustrate the idea of an ensemble technique. So let's say that we have two models here, model 1 and model 2, whatever the learner is. Maybe model 1 is a decision tree and model 2 is a logistic regression model, which makes sense based on the thresholds that we have chosen. So one is nicely in the middle there, 0.5, the other one not so much so, but I have two trained models. I have a small example data set that I'm testing out the models on, and I'm looking at their probability predictions. I need to convert those probability predictions into labels, yes or no. I care mainly about accuracy here for the sake of the example, right? So I'm just counting the number of times that my model gets it correct. And I am deciding on the best thresholds for both of these models individually. Well, you will find that the best threshold for model 1 is 0.54, and for model 2 is 0.50. You can try other thresholds, you will see that that's the best that you can get. You will at least always make one mistake. So for model 1, the mistake is made here. For model 2, the mistake is made there, right? So you can't get better in terms of using these two models individually. Well, what you could do is then say, well, I can define some sort of meta model. Why not? It just becomes part of my overall pipeline, right? And it doesn't have to stop at one singular learner necessarily. So you just say, well, I'm just going to take these two probabilities that I have here as some sort of intermediate features, if you will, intermediate steps, and I'm going to combine them in some way. Well, how? We can play around with a couple of techniques that we could apply. We could say, okay, let's try taking just the minimum of both probabilities. Let's try taking the maximum. You can sort of imagine that if you would have not two models that you want to combine, but 5, 10, 100 models, that min-max is not going to be so stable. Or we could say, well, at least let's take the mean, right, the average. That seems to be like an easy approach there. Okay, so that basically means that your final result now, depending on whatever approach that you take to combine these probabilities, will be again a final probability there. So that's now your overall model. Your overall model is now a combination of two probabilities that are being fed in by two underlying trained models. Again, same question, you need to determine a new optimal cutoff, right? So, which is not necessarily the cutoffs that you had originally for these two models. So again, you go over your sweep of cutoffs to utilize, given that accuracy is here the thing that you care about. And lo and behold, both for the minimum here, you can find a cutoff, and also for the average, again, which is the more realistic case, you can find a new cutoff combining these two probabilities that now somehow is capable to score all of these cases correctly. So now, in the mean column, I don't make any mistake anymore. So just by this trivial example, you can kind of see, well, somehow indeed, if I have two models and they're both not perfect, but they're not perfect in the same way, so they do make mistakes, but they don't make the exact same mistakes. They have different subsegments of my data set that they are good in versus not so good in. Well, then a combination, even a simple combination of their both outputs, can already lead me to something that works better. So that's that increase of performance as we just introduced before. Now you might say, well, if I increase the number of models that you have, then min is not stable, max is not stable, and median, average, overall, it might start to become a bit more washed out. So which other types of combinations can I make between several models that I have? Well, another very commonly utilized approach is a voting-based approach, especially once you enter or you bring in more models into the mix, where you also have different options. Like in the first option, you have 6 models, and as we will see later, these 6 models might all stem from the same algorithm or the same learner. And you basically do not expect them to give you raw probabilities anymore, as was the case here, but you just, and you combine them in some way, but you just expect labels. So for each model, you ask them, okay, do you think that this is a positive case, or do you think that this is a negative case? And then you tally their votes, and then basically the majority wins. So in the first example, 4 out of 6 models say that this is a positive, a yes, so yes would win. And again, now, because you have kind of hidden out what all of these underlying models do, right? At the end, you might still want to rank your individual cases. So the question is, okay, yes wins 4 out of 6 according to my majority vote. Can I still assign some sort of probability then on my final output here? And as you can imagine, in this case, you can still do so. Just as in the case of a single decision tree, we were able to put a probability based on counting the number of yes-no train examples in the leaf node where a new case ended up in. Also here, we would be able to say, well, if you do want a probability, I would basically say, well, the probability of this case being a yes is 4 out of 6, because 4 out of 6 models agree, right? So again, your probability becomes less and less calibrated, right? But if you do want to rank, you can kind of imagine, well, if you have 100 models and 99 of them agree with the outcome, that's a stronger prediction than if only 55 out of the 100 agree with that. Now, a natural question to ask, if you set up some sort of voting scheme, you might also wonder, well, perhaps you have models in there, if they are not all of the same learning type, they are not all decision trees, but maybe you mix a couple of models together. Maybe you do know, or there is some way to know, that some of these models are, well, maybe a bit stronger than other models. You still would like to combine the weaker models because they can still give you a little bit of improved performance, but you do know that there are models that are better than other models in here. So you just don't want to give each of these 6 models 1 vote. You also want to weight their votes, basically, right? And in that case, you can basically reach an outcome where you say, well, model 4, even although 2 out of these 6 models, they predict no, but I do know for some reason that model 4 is a very strong model, I might want to give it more votes so that at the end, the no case in this situation would still win. And then we can actually go back to the previous setting and we can say, well, if I do have the raw probabilities that all of these 6 models output, Basically, what I'm trying to set up here is a linear combination of those probabilities, right? I just multiply a weight with every probability that the models output, and I sum them together, and that's then my final probability. But then your question will be, well, either how do you determine the weights that each of these probabilities or each of these models get, or in this case, how do you define the number of votes that all of these models should get? And obviously, typically, we don't have a way to do that. That will involve that we need to learn those weights, and we need to learn the number of votes that each model gets. So that would be a learning step in itself again. And that's typically described as meta-learning. You're learning something about the learners. And in this case, you're learning something about the strength of each of the individual models. You're learning how to combine them correctly. Crazy? Well, no, not really. This is exactly what is sometimes done. You have a couple of ways to set this up, either in a mixture of experts style format or in a stacking style format. Stacking is a bit easier than mixture of experts. But what you see here with the mixture of experts model, which is already a quite old approach, but it still works independent of whatever the classifier is that you utilize. What this thing basically says is, well, you do have a couple of models, C1 and C2 and so on. No matter what they are, doesn't matter, as long as they provide me with probabilities. And then I have a new case, right? Or I have a bunch of cases on which I want to apply this meta-learning on. I give it to all of these classifiers that I already have trained, and I know that they will output me with probabilities. They will give me back probabilities, hypotheses in this case, but basically probabilities. And at the end, I want to combine them in some way where my final probability is just a linear combination of weights that I need to train times the individual probabilities that these models output. Okay, then the job is I need to basically learn the weights for this combination. And in the setting of a mixture of experts model, you can basically apply different techniques on this. You could use something like a stochastic gradient descent, why not? But traditionally, what has been used or what is used is the expectation maximization or the EM algorithm. But basically an iterative procedure to learn or to figure out what the weights should be that all of these classifiers get. That can work. What is the drawback, obviously, is, again, we spoke about interpretability. You can kind of imagine that now this final output that you get here is not very interpretable anymore. You do know that it's a linear combination of individual models, but to kind of talk your way through this, let alone that you would try to apply something like Shapley values, as we saw last time on this, becomes a little bit harder, right? Because now the underlying model is basically a combination of several models. So in most real-life production contexts, this is not typically utilized in this way, or this kind of ensemble modeling is not typically utilized. On the other hand, where you do see it still popping up quite often is in competition scenarios. When people play on Kaggle, for instance, this is still relatively common that people try to either mix models together like this or stack models together like this. And speaking of stacking, that's then the other kind of approach that you can take. And that basically says, well, you have a couple, again, of classifiers that you have already trained, and you're looking for another way to combine them. Before, that combination was a linear combination of which you had to train or learn the weights for. But what we could also say is, well, given a data set, and these things provide me with probabilities, why couldn't I just utilize those probabilities again as features in a new meta-classifier that I will construct? And basically that is very similar to what we already did here, where we said, well, these two are probabilities, and then, well, the meta-classifier here was just a fixed parametric thing that we decided, like just let's take the average, or just let's take the minimum or the maximum of both. But you could say, well, let, again, a classifier figure out how it should use those inputs from those individual models more directly. And then you end up with this. So basically what you will train this meta classifier on is your feature vector will now just consist of all the probabilities that these individual classifiers provide you with. Your label is still the same label that you started with, right? And then this thing's job will be, And if you utilize a linear regression or a logistic regression here, it will basically boil down to a linear combination anyway, but you could use whatever your favorite classifier is there to basically learn how it should combine the different probabilities of those submodels that you have. And it can become additionally interesting in this case, or something that you can do in this case, is the feature vector that you provide to this meta classifier might not only need to consist of, I have my original probabilities coming from my original classifiers P1, P2, P3, and so on, right? And then I still have the same label, in this case either yes or no, that it needs to predict. But then the best you can do is, again, some sort of combination, maybe not a linear combination, but still some sort of combination between those 5 probabilities that your original classifiers output. But another thing that you can do with this setup is you can take the original features that you had, right, for your data examples, feature 1 and so on, and also include them again in this meta classifier. And then what you're expecting, or what you're hoping, is by combining that information, is that the main role of this meta classifier will be to learn, not again the classification task, because your subclassifiers have already done that, but is to learn, can I figure out in which segments of the original population described by your original features, can I figure out whether I should pay more attention to one of these particular classifiers that you gave me? Maybe I can see that there is some link between a feature and one or the other classifier is then doing better in that subsegment. Of course, then your meta classifier itself needs to have a sufficient complexity to learn those patterns, right? Can be interesting in cases where maybe your subclassifiers need to be relatively simple or interpretable, but then you still want to combine them in some way using a more stronger or more complex meta classifier. No matter what, at the end, if you would have to inspect this overall thing, same thing, you do have a loss of interpretability there, right? And you do have an additional production strain as well. Maintaining this whole system will be harder than if you would just have to maintain a singular classifier in this setting. But again, this is still not so common in practice, but it's still very common whenever people really want to squeeze out very small percentage points in competition settings, for instance. So this concept of stacking and combining models together in this way still finds a use in that setting quite often. And then another kind of exemplary technique would be the one of smoothing, which is also a bit of a weird one, but can have benefits in practice at least, where you say, well, I know that for my data set, I could tackle this using a very simple linear model, like a logistic regression, which is basically, again, in the two-dimensional case, cut a line through my data set. And I know that this thing is not perfect, right? It misses a whole lot of red examples that just fall outside of the decision boundary. So normally, I will not really utilize this in practice. But then I can utilize something like a decision tree that I've trained. I have not overfitted it, so I did apply early stopping or I did apply pruning. This thing works way better, is capable to reach a way higher accuracy level because it identifies more of my red cases that I have in there, but might be a bit, well, I want to still make this a little bit more robust. This might still be easy to explain, but in terms of robustness, especially going towards the future and in the extrapolating case, this is not yet perfect. For instance, if tomorrow I have a case which is over here, you might expect that since it's in the expansion of this red tail over here, that a normal model would also predict if tomorrow you have a new case there, then it's a red case, right? In the case of this decision tree, it will not. It will tell me that it's a blue case. Why? Because it didn't see any training examples that fall in that region. In that case, it would just default back to the majority outcome, and the majority outcome in this case is blue. So I might say, well, do I have a way to maybe, and I also don't like the fact that these orthogonal splits, they maybe are not so robust, and again, this is a toy example in the two-dimensional case, it doesn't really matter, but I would like to avoid kind of issues, sensitivity issues going forward. I know that nothing is perfect, and at some point I will have to retrain my model, but is there a way how I can make it a little bit more robust against these potential new cases going forwards in the future? Well, again, quite simple. You can say take a lambda and take the probability of your logistic regression model times lambda, plus the probability of your good model times 1 minus lambda, right? Lambda will typically be quite small in this case. Tune that lambda value with an additional cross-validation run that you do, and then your combined decision boundary will look something like this. And basically, it's called smoothing because you can see that just by applying or overlapping a linear decision boundary on top of a more complex model smooths out the decision boundary of that more complex model. And then you're more protected against either cases that might show up over here in the future, but also your decision boundary itself is smoothed out a bit further. That maybe has a bit more of a practical use than the other two cases that we saw just now. But in any case, none of these, so either smoothing or mixture of experts or stacking or combination rules, all of these are still at the end of the day a relatively manual approach, right? So we have now kind of proven that, okay, yes, a combination of models does make sense, both to increase performance, and this already reveals perhaps also to increase the level of generalizability of these models as well. But instead of doing this manually, do I not have a way that I can set this up a bit more in an automated fashion, let's say? Or in other words, isn't there an algorithm that when I run it, the outcome, the model that is being trained, is itself already a ensemble style of thing, is itself already a collection of submodels without me having to go in manually and maybe combine logistic regression with a decision tree with something else, just in its own or by its own nature. And that's then what you end up in terms of two key strategies that you can apply of how you can set this up. And one such key strategy is called bagging. The other one is called boosting. So these are the two main techniques that you can utilize to create ensemble models directly. So what is bagging? Bagging, the name, well, you bag a bunch of models together. That's already, well, already tells you we will create a bag of different models working together. But the name bagging actually stands for bootstrap aggregating. So we'll have to explain what bootstrapping means. Aggregating, that is a bit more understandable. Aggregating, we just aggregate, we combine them together. So bootstrapping will be the main component here. And it's basically a very simple approach in that sense that no matter what you want to utilize as your base learner, this will work. So your base learner, every individual model that you're going to put in this bag, so we're going to make a bag of 100 models, what each of these 100 models should be, you can choose this. You can even say, well, let's use logistic regression for this. Right? In the majority of cases, we use decision trees for reasons that I will tell about in a second from now, but it doesn't matter what technique you would utilize. You can make a bag of any sort of learner, SVMs, logistic regression, whatever you want. Right? Now you might say, okay, I have a piece of training data, I have 100 examples or 1,000 examples, and you tell me use logistic regression or you tell me use decision trees, so you create 100 different models on the trained data. What's going to happen if you do that directly on the same trained data? Of course, you will end up with 100 identical copies, right, of the same decision tree, of the same logistic regression model with the same coefficients. So an aggregation or a combination of those models would not make a lot of sense, right? Who would like to have 100 identical models that basically is the same as just using one of those models directly? So instead, we're going to apply a trick, and the trick we'll apply is, well, we're not going to give the exact same training data to all of those 100 models that I have in my bag, to all of those 100 models that I'm going to train here. I will add in a bit of diversity. Diversity basically even meaning a bit of randomness in there. That sounds strange at first, but we'll see later on why that works out. So the key thing is that I will not train 100 models in my bag on the same exact data, but I will add diversity to my data set so that they don't get the exact same copy. And in the case of bagging, and that's where this bootstrapping comes in, the way how I can create this diversity, let's say I use decision trees and my bag, I'm not going to draw 100 decision trees, so let's say my bag consists of 3 decision trees that I have to train, And I have my original data set consisting of, let's say, 6 instances to make it easy. So 1, 2, 3, 4, 5, 6. What I can't do is give the same data set to all of these 3 decision trees, because I would end up with the exact same copy. They would predict me the exact same thing. If I use early stopping in them, they would give me the exact same probabilities. No matter if I try to aggregate them, that wouldn't work. So I'm going to add in diversity. So I'm going to give each of those 3 trees a bootstrap of my data. And originally, the way how this was devised, right, is to say, well, how many instances should be in each bootstrap? The same number of instances that you have originally. So you had 6 train instances originally, so we're also going to make a bootstrap that consists of 1, 2, 3, 4, 5, 6 instances there as well. I'm going to randomly sample instances. Yeah, but wait a second, if you randomly sample 6 instances to create a set of 6, yeah, you will end up with the same 6 instances again, right? So that wouldn't work. Ah, but wait, bootstrapping samples with replacement. So it will pick 6 instances, but there might be copies in there. Instance number 1 might appear twice in the bootstrap, causing that maybe instance number 5 does not appear in the bootstrap. And those are the data sets that I give to each of these 3 decision trees. Once that I have those decision trees and they're trained, now my final model is immediately after training a bag, a collection of decision trees. Now I have a new instance, let's say. Right? Tomorrow I want to utilize this in production. So I have a new feature vector. How do I predict? Before, in the case of a single decision tree, I would feed this instance to that single decision tree. It would go through its steps. And depending on the leaf node, it can give me a probability that y equals 1. Now all of those decision trees will give me a probability that y equals 1. How do I decide the final outcome? Well, one way that I can apply is to use something that we just saw. I will somehow set a threshold to convert each of the individual trees' probability to a yes-no outcome. So let's say only the first one says no and the 2 others say yes, and I majority vote. So my final prediction, I have 2 out of 3 decision trees in my bag agree that it's a yes. So my final prediction will be a yes. And if I do want to assign a probability on that, well, one way how I can still do so is say, well, it's a probability with 2 out of 3 because 2 out of the 3 members in your bag agree on that. In bagging, it is the aspect of diversity that makes the ensemble work. We'll immediately see why that's the case, right? It might sound strange that by just randomly messing with your training data, that this helps somehow to reach, well, either better performance or reach better protection against overfitting. In the case of bagging, as we'll see, it's mainly protection against overfitting, but we'll see why that works. But it's the diversity aspect that helps here. Are there other ways how you could introduce additional aspects of diversity? Yes. In standard bagging, no matter what the algorithm is, either logistic regression or decision trees or whatever, the one piece of diversity that you need, the key one, is bootstrapping, is sampling with replacement. Should you want to add in additional pieces of randomness or diversity, you can. And that's exactly why there are different algorithms, exactly because they add in additional pieces of diversity, as we will see, right? Why do we tend to utilize decision trees so often in this case? Like I said, you don't have to. You can use logistic regression. But very often you will see that in bagging algorithms and also for boosting, that decision trees are the base building block to put in the bag. 2 reasons. One is because they have generally very nice properties. They are safe against outliers. they don't worry too much about missing values. You might have to treat them, but they are non-linear, so they can each individually spot interesting patterns or deep complexities. They can fetch out interaction effects and so on. So they all work pretty well on that. Another reason, as we saw with decision trees, is that they are extremely unstable. As we saw, even just a slight perturbation of your train data will cause that your trees might end up looking wildly different. Well, here we are doing exactly that. Every decision tree gets a slightly perturbed bootstrap of the original data and hence will end up looking quite different, right? Which is exactly the property that we want to exploit here. So that's also why we tend to utilize decision trees in this setting so much. Other techniques like logistic regression, they will also work, but they're more stable, and that's exactly not what we want here. We want to have the diversity being present here, both in the learner by it being unstable and by perturbing the data set at hand. So this is basically the same thing as what I just drew. So we use bootstrap aggregating to create perturbed copies of the original data set by using sampling with replacement, and then you just train, not 3, but typically you train 100 decision trees. And then you combine them using majority voting. Well, majority voting, there is something to say for that, right? So you might wonder, if you utilize majority voting like I expressed, the step that we would need to do is we would have to take the probability of each individual decision tree and convert it into a yes or no outcome, right? That might cause you to wonder, yeah, but wait a second, what do you utilize to convert, if you have 100 decision trees, what do you utilize to convert the probability output of every individual tree to a yes-no outcome that I have to utilize in majority voting? I need to determine some sort of cutoff. And we know from before that using the standard 50% cutoff for decision trees doesn't always make a lot of sense because they are not well calibrated. So there might be another cutoff that we need to set, right? And even more, because now I do not have a single decision tree, but I have 100 of them, does that mean that I need to determine that cutoff for all of those trees individually to convert their probability to this yes-no outcome that I should utilize for my majority voting approach? Well, luckily not, right? For a reason that we will see also in a second from now, there is something that will help us to avoid setting cutoffs. But still, what you could also take as an alternative, you might say, you know, why don't we make it a bit simpler, and instead of using majority voting, and then I utilize the number of members that agree out of the total members in my bag as my final probability, why don't I just take the raw probabilities that all of my trees output, and without setting cutoffs and converting them to yes-no outcomes, why don't I just average them together? And that's then my final probability output. And then you set your cutoff on that final output in whatever way that you want, just like before. And that's typically today the common case, or that's what the majority of good implementations do. So the default, for instance, in scikit-learn is exactly taking the average of the raw probabilities instead. In the original publication of bagging-based techniques, it still utilized majority voting, and it did it that way instead. But things such like scikit-learn, they just say, well, don't convert it to a yes-no outcome, just take the average of their individual probabilities, which is also a bit more stable, because instead of then your final probability being how many members agree out of the total in your bag, your final probability is at least an average of things that themselves are probability predictions. Yeah, what about the case of regression, right? We saw before that you can also make decision trees that work on regression problems. Do they also work for bagging? Yeah, they do, same thing. You give each tree a bootstrapped version of the data set. So you sample with replacement. And remember, the output of each tree in this case is not going to be a probability, but is nevertheless, or is in any case going to be some kind of continuous value. Well, in that case, you have made it simple, because same thing, you also average those individual predictions, just as we do in this case or in the modern case for probabilities. So then at least those two cases are equivalent. It's not, for classification we use majority voting, and for regression we average. No, we just average the predictions of the 100 trees that we have. Now, an unanswered question is, no matter whether you use majority voting or you would use these averaged probabilities, you would see that if you then plot your ROC curve, for instance, on your test set, that they are mainly equivalent. They don't give such different results. So even if you still have an older implementation that uses majority voting, why is this an equivalent result, right? That's still something that we need to figure out. And that seems strange in the beginning because in the case of majority voting, we do need to set cutoffs for all of our trees to convert their probabilities to yes-no outcomes. And we haven't answered yet, but do I set a global cutoff? And in that case, do I use 0.5 or do I need to tune that for each individual tree, right? Which is typically not something that you do. So we'll answer that in a second. Now, there is an interesting other thing that you can apply with bagging, and that is that they give you some sort of intermediate validation result for free. Not saying that you should not use a test set, that's always a good idea, so this doesn't kind of alleviate you from the fact that you should use a test set, but this gives a very easy method at least, or an easy opportunity to already intermediately get some idea of the generalization power of this ensemble of trees that you have built here. And that's by something called out-of-bag validation. So normally what you would do on your original train data, like we did before, we could again say, well, take every instance, pass it through all of the decision trees that I have, get their probability outputs, and average them. So I get my final prediction for each of those cases, which is just the averaged individual probabilities of my 100 trees. And then on this, I can plot my ROC curve, but because I'm using my train data, I might expect that this ROC curve is going to be extremely good, right? Because probably these trees have all managed to fit my training data quite well. But what I could do is I could realize, well, if I look at the bootstraps that I took here, and because I'm sampling with replacement, like I said previously, instance number 5, just by random sampling, did not show up in the bootstrap of this first decision tree. So what I could do, instead of saying, well, for every instance in my train data, pass it through all the trees, why don't I pass it just through all the trees that did not have that instance in their bootstrap? So it is as if I'm only using the trees in my bag, not all 100 of them, but I'm only using a fraction of the trees that did actually not see that instance in their train data because I bootstrapped my train data. And I get their probabilities, I average them, and I make my ROC curve based on those results. So for every instance, now I'm only asking the trees that did not have that instance in their bootstrap. So I'm doing an out-of-bag validation, OOB validation. And that's already a very good initial validation check. Again, you will still need an independent test set though, but that's something that you get for free here. So that's bagging basically. What is the technique that implements bagging? Well, we have basically almost fully described it already. There is only an additional thing that we need to mention here, but the quintessential technique that applies this or utilizes this concept is called random forests. Forests because it uses decision trees as its base learner, just as we did here. Random because it introduces randomness to increase diversity in the building of those decision trees. It uses two pieces of randomness, and one of which we have already seen. The one main key piece in terms of adding diversity and randomness is bootstrapping, sampling with replacement. Random forest says, well, this works, but we're going to introduce an additional piece of randomness to increase diversity in those individual trees that we built even further. Okay. So it constructs a multitude of decision trees. It applies bagging, So one part of randomness comes from bootstrapping. Where does the second part of randomness comes from? For every individual tree that I'm building, I zoom in on one of those trees. Every time, I'm wondering what is the best candidate split to pick here. And remember, that's the exact same thing as before. We calculate information gain on all the possible splits that I can do. Remember that before, the way how we did that is for continuous features, we check the values that I have in my train data, or the halfway points, and I basically ask, is this greater or equal than this value? Yes, you go right, left, you go no. For categorical features, is this feature equal to this level? Yes, you go right, no, you go left. Well, to introduce an additional piece of randomness, every time we are evaluating a candidate rule, or we are trying to pick the best candidate rule, instead of considering all the features that I have in my train data, I consider a random subset of features. Not with replacement for features that doesn't make sense, right? I just consider a random subset of features. Features, right? Meaning that, remember, if I have temperature, I will ask, are you lower than equal to 20, 21, 22, and so on? Humidity, are you equal to high, and so on. Well, if I say I can only randomly pick one feature, that would be the extreme, right? Subset can be one. Well, temperature, you're not even going to consider all of those splitting points. And that's the additional piece of randomness that random forests introduce. Now put it between your ears. This random subset of features is sampled every time a split has to be decided or has to be made. It's not the same subset for the overall tree. It's every time we split that we take a new random subset of features, right? So this is per tree, per split, not just per tree, right? Per tree, per split. Could you do it per tree? Well, yeah, you could do that as well, but here they decided to do it per tree, per split. And we will see that by doing this, by adding this diversity, we mitigate the effect of overfitting so much, we are capable to generalize way better by using this bagging approach with diversity, that now all of those individual trees that we construct in our random forest, we can have them grow all the way out. We don't need to apply pruning anymore. We do not need to apply early stopping anymore. And this reveals why the decision of those tree cutoffs that you have to make there is actually not a big deal. Because if you now have every individual tree grow all the way out, given that you have enough features, and you will have, it's extremely likely that all of your leaf nodes in those individual trees will be pure, right? That's exactly what a fully grown tree did. Meaning that actually every individual tree, if you think about the two probabilities that it can actually output, in the case of binary classification at least, are only two outcomes. It's either 100% yes, or it's 0% yes, because my leaves are pure. And if those are my two outcomes, I don't even have to set a cutoff. And I don't even have to set a cutoff for individual trees either, right? And that's why I don't need to bother with setting those cutoffs. Now, that being said, some implementations will still allow you to say, well, even for the individual trees, I do not want to make them fully pure. I still want to stop in between, mainly for the reasons of computational efficiency, of speed, right? No technical reason anymore in the sense that, if you don't do this, your random forest will overfit. No, it won't, but just to speed things up. In that case, indeed, your individual trees might again be producing probabilities. And then you have two choices. In the case of majority voting, you just use 50% for all of your trees as your cutoff, or and hence why scikit-learn decided to do it this way, you just say, nah, in the case that they are not pure, average their probabilities. In the case where they are pure, right, when you do an averaging of their probabilities, and their probabilities are either 0 or 1 anyway in that case, that's why you end up in exactly the same situation as the majority voting case. Because then you're just taking an average of counts again. And then 2 out of 3 trees agree, 2 probabilities are equal to 1, the last one is equal to 0 in that setting. Some remaining questions. Well, which hyperparameters does this thing have? Well, basically 2. One is how many trees in this bag, in this random forest. As we will see, there is no risk of overfit. You need a sufficient amount of trees, but at a certain point, if you continue to add more trees, it won't harm you. Yeah, it will harm you that you spend more time training those trees, and if you want to use that model, instead of asking 100 decision trees what they think, you need to ask 500 of them. But okay, other than speed, it won't harm you. So just use plenty. If you use old versions of SAS Enterprise Miner, then you might end up with 10 trees, which is way too little. Scikit-learn for a long while utilized 100 as their default. I think by now they're already at 300. So use 300 trees. What should be the depth of each individual tree? Like I said, you don't have to prune. Let them grow all the way. You can still apply pruning or early stopping to speed things up if you want, but you don't have to anymore. Not for a single individual decision tree model, but now the fact that we bag them, now we're free of the pruning aspect and the early stopping aspect. The size of the bootstrap. Like I said originally, every bootstrap had the same number of instances, 6 in this case, as my original data set, but I sample with replacement. Now you might say, yeah, but wait a second, if I have 2 million instances to begin with, why would I have to make every bootstrap 2 million as well? That's also going to slow down training, right? So indeed, this is mainly a decision that comes from early days where we might not have sufficient data. If you do have sufficient data, you can make your bootstrap sizes also smaller, right? Don't resample the same amount as you had originally. You can also try to add in more diversity by making that a bit smaller, right? Don't sample 10, huh? You still need sufficient instances, but if you have a whole lot to begin with, you can make that smaller. And then the other one is big M in this case, and that is, well, what about the number of features that we randomly sample in every split of every tree? What should the size of that subset be? You can decide to sample all of your features, then you're basically back to the default bagging mode, right? And you remove that piece of randomness. The other extreme would be to, at every split, just sample one feature randomly. It will be a different feature at every split, but you just randomly pick one feature, and yet, let's say temperature, and then you decide, okay, what's the best splitting point for temperature? And we pick that one. There is a heuristic that is typically applied and is different for regression and for classification. For classification, you take the square root of the number of features that you have rounded down. For regression, you take the maximum between n divided by 3 and 1, n being the number of features that you have. These tend to work quite well out of the box. That's typically the only hyperparameter that you do have to tune in a cross-validation run, if you do want to increase the efficiency of your random forest a bit further. Other than that, this is an extremely versatile, easy, simple, powerful technique. Because decision trees don't require much pre-processing, also the random forest as a whole will not. Question?
I have a question regarding the bootstrapping. So you mean that not all instances can be present in the bagging?
That's by default, yeah. Yeah. So again, you're sampling with replacement. So if you have instances 1, 2, 3, 4, 5, 6, your bootstrap might have 1, 1 again, 4, 5, 6, and let's say 6 again.
But in total, like
the size.
The three trees,
Yeah.
They would need to have at least one instance from sense of like the two would need to be represented in at least one of them.
Since yeah, I see your question now. Like, does every instance have to be represented in one of the bootstraps? You know, if you're building 100 decision trees, it's quite likely that they will all show up somewhere. But to be honest, that's not checked at all. So it might indeed be that you have an instance from your training data that you're not utilizing in any of your bootstraps.
Since the objective is to have as much diversity as possible.
That will even increase the diversity even further then. And on top of that, if you do then your out-of-bag validation, then those instances that do not show up in any of the decision trees, then those will be evaluated by all of the decision trees if you do that validation. Yeah, yeah, but good question. Yeah. The only thing that you do lose out, again, is interpretability. Before I could tell you I can make a slide with one decision tree and you can bring that to your manager or whatever. Yeah, now your random forest, it's still explainable. You can say, well, to know the prediction of this model, you ask each of these 100 trees individually and you average their probabilities, so you have a book of decision trees. But not easy to explain anymore. So again, you will have to fall back to utilizing something like Shapley values now, like we saw last time, to explain the random forest as a whole. This idea has been extended. Typically what people utilize nowadays instead of standard random forests is something called extra randomized forests or extra trees, as it's called in scikit-learn. Some implementations like to talk about random jungles and so on. But extra trees gives you an additional little boost by adding in another piece of randomness in this setup. So we had bootstrapping as piece number 1. We had random subset of features as piece number 2. What extra trees does is it says, yeah, but given, let's say you pick temperature as a feature to consider in one of your splits, you will still evaluate all of the possible splits for temperature. Why don't you randomize that as well? And that's what extra trees does. It also takes a random subset of splitting points as well for those features. Tends to help a little bit more than standard random forest as well. Even going further, not so much for supervised techniques, but we will see later on an application of this, you might say, well, what if we go completely crazy with this idea? And for every individual tree, every time it needs to consider a split, what if I say take one random feature, and for that feature, take one random splitting point? So no information gain even to calculate anymore, because you're not comparing any of them, you already just randomly pick a splitting point. Would that work? For classification, maybe not so much, because you lose kind of the supervised guidance there, but we will see later on an application of these random forests that do exactly this. In every tree, in every split, one random feature, one random split. Just eyes closed and pick something there. So that's also possible. So that was bagging. Next up then, boosting. The other mindset or the other angle that you can take to create ensemble techniques, a set of trees, if you will, at the end of your algorithm run. Now, boosting sounds way cooler than bagging, so that's also maybe the reason why it's the more preferred one nowadays. Boosting also creates an ensemble of classifiers which are combined, just like bagging does. But it does not use bootstrapping. It does not perturb your original training data, sampling with replacement. It does not use bootstrapping at all. And instead of having an approach, as we saw in bagging, where you could say, well, once I have created my bootstraps, all of my 100 decision trees, they can actually do their own thing. They can train in parallel. If I have 100 computers, all of these 100 decision trees can be trained in parallel. They don't need to know about each other. Just at the end, I combine them. You send them back to a central place. In boosting, that's different. In boosting, that parallelism will be lost, and we're going to build up our ensemble in a stepwise manner. We're going to introduce new trees to the collection step by step, sequentially, one by one. So I start with one tree, and then I will add in a second one, third one, and so on. And every tree, or whatever the model is, but again here, same thing, it will typically be decision trees. Every tree that I put in will be focused in some way, will be pushed towards fixing the mistakes that the ensemble is making so far. So if I already have 10 trees, tree number 11 will be pushed in some way to focus more on correcting the mistakes that those collection of previous 10 trees are making so far. So here, the main idea will be about cooperation and correction, rather than diversity. So every tree that I add in here will be geared towards focusing on correcting the residuals, if you will, on cooperating with the previous ones. So not about diversity. That also means that instead of looking for angles to increase diversity like I did before, and potentially from the idea of I want to protect myself against overfitting and boosting, it will mainly be, well, if you have some sort of weak classifier, but you introduce them gradually on top of each other, you can get strength thanks to that cooperation. But you might risk into getting up into overfitting territory again, as we'll see later on. Okay, what's a simple way how we could do so? Well, my first model is going to be a single decision tree. For that, well, nothing special. I have my training instances. I don't use bootstrapping, right? So that's out of the picture here. So I just say decision tree, here are the training instances, please go. And you can already feel, well, here in this case, if you talk about mistakes, what I probably cannot do is say, well, this first model that I'm going to build, I'm again going to build that decision tree all the way down, right? Because then, very likely, that this decision tree fits that training data perfectly. There aren't any mistakes left to make or to correct on, right? So here, by the nature of things, if I do that, I'm back into overfitting territory. So I will say, well, I, in this case, will again constrict my decision tree to say, don't go too far. Right? Only a couple levels, or use early stopping, or use pruning, or whatever, but now I can't build them all the way down anymore. So given that, I built my first decision tree, now relatively small, so it does make mistakes. I can then take that decision tree, score it on my training examples, and then I say, okay, the next decision tree that I add in, I need to have some way to have it focus more on the instances that I'm making mistakes on thus far. Right? In the beginning, every instance gets the same weight because I don't have any model yet, so all my instances are as important. But from the moment I have my first decision tree and I calculate whether they're doing correct or incorrectly on my train instances, I can score, I can weight my instances that are not being predicted correctly yet. Well, okay, I can do that, but that still means that I will have to push my next learner that I add to focus more attention on those cases. What do I do once I do that for a couple of times, and let's say in the end I end up with a collection of decision trees and I have a new instance, I want to give it to that collection, same thing as before, right? Again, I use majority voting, or I just take their individual probabilities and I average them. That's how I do inference. So the main step here lies in the training, that I will have to assign weights to my instances and then push my decision tree to take those weights into account somehow, that it pays a higher attention on the train instances that are thus far predicted incorrectly. We already saw a simple way how we could do that when we spoke about sampling, undersampling, oversampling. We also spoke about instance-based sampling rather than class-based sampling. And I told you, well, you can always do it on the data level, right? If some instances are more important than others, you can just literally copy them in your data set. We could do something similar here. We could say, well, if we have an instance here that so far is not being predicted correctly yet, we will just increase the number of copies for that instance, and that will cause that decision tree pays more attention to that instance. But that's not very elegant, but it basically boils down to the same thing. So the quintessential implementation of this idea is something called AdaBoost. Couple of things here. It trains, again, an ensemble, a collection, not unstable, but weak learners. That's quite important, that these things are weak. If they would be strong, then already the first model will overfit the train data. That's not what I want. So now I need to constrict my models a little bit to be on the weakish side. Every instance in the beginning has the same weight, because I don't know anything yet, so just 1 over the number of instances that I have, which is line number 1 in there. And then over a couple of rounds, I will introduce new learners in there. And basically what AdaBoost says, well, here is a way how you can assign new weights for the next round. It's basically the previous weight times e to the power of this alpha thing times the prediction of your model. And this alpha thing is basically set to be this. Okay, good. And then your learner itself, your decision tree in this case, will also have to incorporate, so there will also have to be an adjustment to the way how you calculate information gain to take those weights into account. Or alternatively, you just copy the instances based on the weights that you gave. That's a bit more messy or a little bit less elegant than this bagging idea that we had, but it also works. But you might wonder, okay, but the way how these weights here are calculated, that seems to be just like in a bit hand-wavy way given. Yeah, indeed, it works. So afterwards, there were some people who were looking at this and they say, well, can't we generalize this a little bit further? And so Friedman said, well, after some, and it's mainly a mathematical result, it's not so important to memorize or to what's said here, but he basically said, well, actually what you're doing here, or your inherent loss that you're optimizing with this sequential approach of adding in learners and this reweighting that you're doing of your instances in every step, basically what you're doing is you're building some sort of additive logistic regression model. If we take logistic regression as, let's say, our base learner, what AdaBoost actually ends up doing is it's optimizing an exponential loss function by means of this strategy. Okay, that itself doesn't say a lot. The next question is more interesting. What if you would like to optimize a different loss function through this sequential building up of classifiers? So you don't want to optimize exponential loss, but you want to optimize something else. Well, with additive logistic regression, like it was set up with AdaBoost, that wouldn't work. AdaBoost was kind of designed to inherently optimize this underlying loss function by the sequential nature. You wouldn't be able to switch this out and say, well, I'm not interested in this, I want to optimize some other sort of loss, focal loss or a weighted loss or learning to rank-based loss or whatever. But there is a way how you can make it work. And instead of focusing heavily on, in every step, how should I calculate the importances for every instance, so if you misclassify an instance, that instance gets a higher weight, and step by step, the longer that you continue to misclassify that instance, the higher that the weight will become. Maybe there is another viewpoint that we can take here. And the other viewpoint is, instead of weighting instances and the classifiers in every cycle, in every step, why don't we tell every classifier that we introduce in every step, instead of predicting the original targets and keeping weights of the instances in mind, why don't we just construct a classifier to predict the error or the residual that the collection as a whole is making so far? And during inference, that still works, right? You just ask your classifier sequentially. The first one gives you a base prediction, and then the other ones in the series, they basically correct on that prediction. The second classifier will say, well, I think that the first guy is 2 units off. And then the third one says, well, I think the collection as a whole is 3 units too high, right? So you can still combine them in that way to give final predictions because they just correct on one each other. So you predict the errors and you adjust accordingly. And what was then shown is that this framework does allow to be more flexible in terms of which loss function or which error function that you want to plug in and that you want to optimize. If you learn sequentially to predict the residuals of the ensemble as a whole. And that makes that boosting is a much more generalistic framework than bagging is. With bagging, we didn't really speak about loss functions, right? We didn't have a lot of ways to play around with that, right? With boosting, we do have a framework where we can plug in our own custom loss functions, which is one of the few that gives us a very easy, strong method to do that rather than or apart from deep learning-based techniques or neural network-based techniques. Also here we have a way how we can both utilize something that's an ensemble based on decision trees, but also allows us to plug in our own loss function. What is still the same though, or didn't change, is that we need to utilize some sort of weak learner, in this case, weak decision trees. Because again, otherwise in the first step, we still build sequentially. We don't want to overfit the training data immediately, then we know that we kind of are in a collapse situation. What do people mean with a weak decision tree? Simply a decision tree that you restrict to only learn a couple of levels deep. In the extreme case, it can even be that you utilize decision trees that only use one split, which is called a decision stump, like the stump of a tree, only one question, basically. That's the extreme case. So gradient boosting fits learners to learn the residual, right? The true target minus the predicted target of the ensemble as a whole. So every m plus 1 attempts to correct the errors of the ensemble that you have thus far. And the reason why this works is because residuals for a given model are proportionally equivalent to the negative gradients of the mean squared error loss function. That's why this is called gradient boosting. You boost on the gradient. You boost in the direction that the gradient of the error function points you to. Meaning, what's the direction that you should move in to reduce your error, as we'll also see in deep learning. Now, here we don't have some sort of iterative procedure to optimize weights directly where we can use that gradient. We can only add in new decision trees. But by telling each decision tree, try to predict the residuals, we are moving in the same direction in our loss landscape as if we would be optimizing weights in a more, let's say, deep learning inspired approach. So gradient boosting fits learners to the negative gradient because we want to point downwards. We don't want to go upwards in our loss landscape. So negative gradient of the loss with respect to the model's raw output. So in this case, we do some sort of functional gradient descent, but it boils down to residual fitting, and that is what makes this work. And then you can plug in different losses and different gradients accordingly. So depending whether you have binary classification or multi-class classification or regression, or you want to use some exotic loss if you're in a learning to rank setting, in the case of recommender systems, for instance, you will find that gradient boosting machines give you options to play around with the loss function that you want to optimize. Now, there is a next step after this gradient boosting, which is called extreme gradient boosting. Now, that sounds even more fun, right, and powerful. When things become extreme means that it's even better. But actually, this is a quite simple expansion on the basic gradient boosting idea. So what we typically do, if there is some loss function that we want to optimize, traditionally you can play around with a weight. Here we can't. Here this is done through the aspect of boosting where every model tries to move in a negative gradient of this loss function, but later we will see that in an artificial neural network we do directly optimize weights. So this is my loss. I start over here with my first decision tree, I add in my second decision tree, and so on. So by moving in the direction, or by predicting the residuals, I'm moving in the direction of the negative loss gradient in this case. But typically what you see is by doing this is a gradient will give you the direction that you should move in, but will not tell you the size of the step that you should take. And this will be an issue, as we will see, when we will train deep learning models as well. Also there we will see that we will utilize our stochastic gradient descent will tell us the direction that we should change the parameters of the model of, but not by how much. So typically in every cycle, we only change them, or we only move the weights or parameters a little bit until we come closer and closer, hopefully to the optimal value, or maybe to a local minimum. That is to be, or that's something that we'll see. That's because the gradient is based on the first partial derivative. Right? And the first partial derivative gives you the steepness of your loss function. In this case, my loss function is just
that one-dimensional thing, but typically imagine your loss function as a landscape. So basically, you know the direction of the step you should take to decrease your loss, but you don't know how much you should step forward in. You can do that based on the steepness. You can kind of say, okay, the steeper downwards, probably the larger the step that I'm allowed to take, but you don't know exactly. If you also want to have more or obtain more information from your error function or your loss function in terms of the size of your step, you need both the Jacobian and the Hessian. Right? You need both the first partial derivative and the second partial derivative. What does extreme gradient boosting do? It says, well, let's also use the second partial derivative of the loss function to inform that optimization a bit further. Then you do not only know the direction, but you also are informed of the size of the step that you need to take. It's that idea to go from basic gradient boosting to extreme gradient boosting is a rather, well, I'm not going to say simplistic, but natural step forward where you say, okay, first partial derivative, second partial derivative, I have more information, I can do my optimization better. Weirdly enough, once we move to the area of deep learning, there we will see that for reasons you might have the same kind of reaction. You use the first partial derivative in stochastic gradient descent. Why don't you also use a second partial derivative there? That might help. And there we don't do that, which is strange. And the reasons why we don't do that is because then all the automatic differentiation frameworks like implemented by PyTorch and so on would not work anymore, or would be way harder to implement. And also because we train deep neural networks on GPUs, first partial derivative is still easy to kind of calculate a backwards computational graph for. Second partial derivative, we say, no, that's too difficult. If you have 20 billion parameters that you need to optimize, that's not worth it. In the case of tabular learning, works well enough, right? So there we can do this. And then you come to extreme gradient boosting, and that idea is today implemented by the major three, right? And the major three packages that implement this are XGBoost, LightGBM, and CatBoost. And still today, if you look at papers, benchmark studies, practice, whatever every industry practitioner will utilize is one of these three. If you're confronted with tabular learning, you don't need to utilize any other algorithm. They're proven. Right? Sorry for the support vector machine people and so on, all beautiful, but this is what every tabular learning case ends up utilizing. And if they don't, it's about mainly issues dealing with regulatory constraints. For instance, in finance, right? Or if you do like investment modeling, there you might still use statistical linear techniques in that setting because those models need to be heavily validated and they are checked by the central bank and so on. Right? And so in those cases, you might not, but in every other tabular setting, you use one of these three boosting frameworks. Yeah? Second partial derivative? Yeah, size of the step. Yeah, yeah, yeah. So normal gradient boosting does only takes the first partial derivative. Now, there are a couple of other things that these packages or that extreme gradient boosting adds on top of as well. First of all, it adds regularization because, again, we do use weak learners, but there is some notion of what's the limit here, right? If I continue to add in my weak decision stumps to my ensemble, can I end up in a territory where I'm overfitting again? And indeed, yes, that is a risk of using these boosting-based techniques. Bagging does not suffer from that. Boosting does. So what can we do against that? Well, playing around with ideas of regularization, right? L1, L2, typically that's expressed on the size of weights, like we saw for logistic regression. Here we have decision trees. They don't have weights, right? But what we can do is we can regularize based on another aspect of complexity, for instance, the number of leaf nodes that I have in total, right? So then I can say, well, if you do decide to add in an extra tree, it better comes at a benefit for my loss that I'm optimizing here, because I'm also going to punish you on the overall complexity of the ensemble, and overall complexity based on depth of tree, number of leaf nodes, number of trees, something like that. And I put that in my loss function just like I did with L1 or L2 before. And this is to mitigate overfitting. Now, what are the differences between these three packages? Well, you can see kind of a comparison here. People have their preferences in terms of what they favor over the other. You could say that XGBoost is kind of the original in this realm. It also implements even some bagging-based techniques as well. Even has support for GPU-based training, existed for quite a while. The only kind of drawback is that your categorical features will still require some sort of pre-processing, typically, so you need to embed them in some way or tackle them in some way. Like GBM, the main thing that it applies to speed things up is instead of going through all the possible splitting points for your continuous features, it first bins them into histograms, and then it goes over the splitting points per bin, which makes it way faster on larger data sets. So if really speed is your concern, you might typically see a light GBM being utilized rather than XGBoost, although the differences are not always that high. XGBoost is also pretty fast as well. But that's why in some industry settings, they traditionally, or some consultancy teams, they traditionally use light GBM on larger data sets because it has speed there. Sometimes with a bit of a drawback in terms of accuracy or performance, but not to say that it's like orders of magnitude. And CatBoost then, that's maybe the odd one out. So it's mainly XGBoost and light GBM that are the two popular ones, but CatBoost falls in the same family, is also quite powerful, and this introduces its own kind of idea to tackle categorical features natively without you having to pre-process them too much. Has some interesting aspects in there. Again, interesting to play around with. You might find that CatBoost gives you a higher performance. It's not as fast as something like a light GBM. The fact that some of the developers are Russians also makes that some people tend to be a bit scared of using CatBoost, but it's an impressive technique. So same of this family of 3 extreme gradient boosting techniques. For the, like I said, for the majority of tabular learning techniques nowadays, if you pick one of those 3, scikit-learn also has some light GBM style histogram-based boosting technique implemented. You're basically okay. Everything else lies in feature engineering and understanding of your data. It doesn't lie in trying out 20 different learning techniques. Just pick one of those, and you can reach your objective, basically. Now, that being said, we also introduced random forests, and I still like them. Out of the bagging versus boosting comparison, I still am a little bit more inclined towards favoring bagging a bit more than boosting is. And that is because of the reason that bagging by nature tries to mitigate overfitting through diversity. Boosting, on the other hand, tries to utilize the strength of cooperation by the sequential building up of classifiers to increase performance, but might lead you a bit back into overfitting territory, hence the need for regularization approaches in here. Right? And the reason why that is, we will discuss going forward, but I think that first it's time to go for a break, unless there are any questions now. Yeah?
Is bagging significantly faster during inference compared to...
It can be, yeah, because you can, well, during inference, no. No, during inference, no, but during training it can be. Because in training you can parallelize the training of your individual trees. That being said, what things such as XGBoost do, they also parallelize the construction of individual trees, because once you have made your first split, the left-hand side and the right-hand side, you can continue to build in parallel as well. But the parallelism is a bit more limited than saying, I want to build 300 trees, I have 300 computers, and they can just do their own thing. So that's also why in big data platforms like Spark and so on, you will heavily see or very often see an implementation of a random forest, because it's trivially easy to scale that up and parallelize that. Yeah. But during inference, it's more or less the same. Yeah. Yeah. Same here. Same for boosting. At the end, you also end up with 100 decision trees, right? That need to predict sequentially to correct the errors of the previous one, but you also have a bunch of decision trees there, so same thing.
Was it more like there's not a way to just determine the size of the tree? The size of the forest? Or?
No, when I talk about explainability and interpretability, it's more like the things that we discussed last time. Like a single decision tree, you can understand for this, if you want to explain an individual prediction or which features are important, you need to grab Shapley values or whatever. You can't look at that bunch of trees anymore. Yeah. Yeah. Any other questions? No? Okay, then time for break. Couple of additional aspects to close off this section on extreme gradient boosting techniques, and there are three main implementations. So like I said, XGBoost was kind of the original one, and if you look, you can check a bit the documentation, but they also implement like a lot of additional techniques that they that have been added in over the years, apart from the basic let's use gradient boosting plus a second derivative plus some form of regularization. Something that was added relatively early on is an idea of applying some sort of dropout, as we will see it also being utilized. We'll discuss what dropout is in the context of neural networks later on. But where they also took this idea of utilizing dropout in the context of decision tree based ensembles. Same kind of idea. Basically the realization that the initial trees that you add in an ensemble when you use a boosted setup tend to be more important than later ones that you add in, and also where you, during evaluation or during training, you try to randomly drop out trees from the ensemble in order to improve the generalization capability of the ensemble as a whole a little bit further. Other things that it allows is, we have seen before that if you have different features that tend to show up in the same pathway of a tree, that this likely reveals that there is some sort of interaction effect going on. Well, here, since we are building multiple decision trees rather than just one, that inspection of potential interaction effects becomes even a little bit stronger if you see the same features popping up in multiple decision trees in the same pathway. This also highlights that there might be a strong interaction effect being present. Well, what XGBoost also allows you to do is to put constraints on this as well, where you say, well, I want to block certain features being utilized together in the same pathway of such a decision tree, because I want to block certain interaction effects, or maybe I want to encourage certain interaction effects from happening. Also interesting is the fact that it also allows you to set monotonic relationship constraints, which is another form of constraint. So where you want to constrain certain features to have a monotonic relationship with the response probability or regression that you're trying to predict. Monotonic meaning that, well, this is not monotonic because it goes up and down basically, but here this is monotonic because from left to right on the feature, it either goes strictly up or it stays the same, or it goes strictly down. Can also lead, if you have some sort of domain constraints that you want to keep in place or that you want to implement. It's nice to see that these additional kind of aspects have been implemented to allow more control over the style of decision tree ensembles that you build. And there is more as well. So what it also implements is learning to rank based losses, which is one of the key benefits of using extreme gradient boosting. Like I said, is the fact that you can modify that loss function, which is not something that you can do easily, at least with random forest. So here, if you're more looking at recommender systems-based approaches or information retrieval-based approaches, where the ordering of the items that you predict matters more than the actual separation between the classes, let's say, which, like I said previously, in many of the cases that you actually see in practice, is indeed what happens, where people want to take a short list of top probabilities or top predicted cases, and where the ordering does matter, that it's nice that you have some sort of flexibility to, instead of using binary cross entropy, let's use something like lambda loss instead. XGBoost, in fact, also implements random forests, which is, again, that's bagging, not boosting, but it has an implementation for that as well. It does have support for multi-output problems as well, which is pretty nice. And like I already mentioned, in later versions, you can even train, predict, and use it on CUDA-based GPUs, so your favorite NVIDIA-based GPU to speed things up even further. So yeah, hence why they have, or why this has become so popular over the past years. Like I said, CatBoost puts a couple of additional aspects on top of that, mainly to handle categorical features by using an ordered encoding scheme, where it also tries to permute the training data again a little bit, so taking some of the ideas of bagging, so to increase the level of diversity a bit, to reduce overfitting, which is one of the let's say, key additions that it makes compared to packages like XGBoost and LightGBM. So if you do have data sets where you have categorical values, especially those with many levels, then some, or in many cases, CatBoost tends to do a little bit better than the other two packages do. Now, taking a step back and highlighting a little bit again the differences between diversity and cooperation. Why does one protect us from overfitting, and why does the other helps us to reach a higher level of accuracy, but maybe perhaps still at the cost of potential overfitting, or us having to safeguard against that somehow. And you will remember from last time that we already had a discussion about bias and variance, right? So where we introduced the two sources of model error, generally speaking, where we said, well, bias basically stems from the model itself not being either complex enough, so not being parameterized enough, or it stems from you not having sufficient training instances, or it stems from the model not being trained for long enough. So whatever you want to put there on the x-axis, we said as well, bias, basically, the model cannot even fit the training data perfectly. And then we saw that as you increase the complexity, that bias goes down. At some point, you will fit your training data perfectly even. But then we spoke about variance, where we said, well, if you would calculate your loss on an unseen piece of data that you do not use for training, in the beginning, that moves nicely down together with bias, right? So your variance is low. Equivalent results between train and test set, but at some point you start overfitting, so your model has now not is not generalizable anymore. It has overfitted, it has memorized the train data, but it is not looking at the patterns anymore. And the reasons why bagging and boosting work feed in into these curves that we had. So if you compare both, what you see is that by the mechanism of bagging, what you do get is you decrease the level of variance, right? So you can take a complex model, so models that have a high variance and low bias. And by combining them in this bagging setup, you decrease the level of variance. And that's the reason why this tends to work well on models that are complex. That's the reason why we said, well, in the case of bagging, in the case of a random forest, for instance, you can now take decision trees that you build all the way down. Models that typically have a very low bias because they fit the training data perfectly, but have a very high variance because they overfit heavily. And the mechanism of bagging helps to reduce the level of variance through the strength of diversity/randomness. They make the models less noisy, and so they increase the variance. Boosting, on the other hand, guarantees that you can decrease bias, but not necessarily variance. So these models, or this approach, tends to work better on models that have a low variance and a high bias. Simple models, low complexity models. Hence, why in the case of AdaBoost and others, especially for AdaBoost, we said, well, we need to use decision stumps, very simple models, right? Now we can't build a decision tree all the way anymore. Right? Otherwise, the first tree that we would fit there would perfectly fit our training data, and then we would get stuck again. In the case of XGBoost or in the case of gradient boosting, typically what gets added in is some regularization parameter on the size of the tree. Right? Okay, you can continue to build your tree a little bit further, but the more leaf nodes that you create, the more I'm going to incorporate that in my loss function. So here it's the strength of the cooperation between simple models that increases your, or let's say that decreases your level of bias, increases your level of fit, but not necessarily variance. So that's that same curve like I drew last time again. So basically, if you look at the figure, if we start from right to left, of course, the middle one is the one where I would like to end up in. Right? I would like to reach both the lowest level of bias and the lowest level of variance, so the lowest overall error. right? So that's that point in the middle of my curve there. Here it's plotted against model complexity, as we saw last time. And remember that actually there is even a second half of this curve where variance goes down again, but with statistical approach, or with standard traditional approaches, you don't observe. That only happens if you have heavily overly parameterized models and a lot of trained data available, which in the typical tabular case, you will never see happening. So we are in this regime. So either, well, we could say what bagging does is we start from the right-hand side. And we say, well, I have a single decision tree that I now built all the way, of which I know I'm on the right-hand side of that curve, my variance is high. It can fit my trained data perfectly, right? So again, if these are my train points, the single decision tree that I have will perfectly fit all of those train points. But I also know that if I would check on test points, well, that maybe I missed the general pattern and it has heavily overfitted there. What does bagging do? Well, through the aspect of diversity, and at a very minimum by using bootstrapping, and by the fact that I use an unstable classifier, each of these decision trees that I now built, their final prediction is going to be the average of the collection as a whole. So what I'm doing is, the second one, it will also fit that particular training data perfectly. But over time, or by adding in 100 of these guys, if I average their predictions, I become more and more robust to noise. I become less and less sensitive to those noisy instances or those noisy labels that I have in my train data. So the average through bagging is going to bring me from the right-hand side more towards the middle side there. If then you end up there and you continue to add in more and more and more trees, which is why the orange line on the slide stops in the middle there, well, you can continue to add in trees in your bag, but it will never magically go towards here, or it will never return back to there, right? That's why bagging is kind of the safe approach. So if you start from a strong learner, like a decision tree, but you want to prevent overfitting, then of course bagging is your preferred technique to utilize there. What does boosting give us? Boosting says, well, no, you start from the left-hand side. You start from a very simple model, a decision stump, or in this case, it's a line because it's a regression problem, right? And these are your instances. High bias, because it's not even capable to fit the training data perfectly. But low variance, because it makes the same high error on both the training and the test data, right? So at least it's dumb in both cases, like we discussed last time. And now, remember, I'm saying, well, I'm picking those instances where currently I'm weighing the cases where you're making mistakes on higher, and I say, well, the next line that I add in, try to predict the residuals of this thing, right? So probably next line will be like this, and then like this, and then like this, and you can see that over time, right, the average combination of all of these models will also move towards the middle. But then the question becomes, or in the case of boosting, we need to ask, what if I continue to add in weak learners and I tell them, well, continue to correct on these small mistakes that are still there? And with boosting, we do see that there is a risk of moving back towards here, right? And that's kind of the pitfall, let's say. That's something that you do need to be aware of. That's also the reason why people tend to prefer XGBoost and LightGBM and CatBoost in practice, because if you want to decrease your bias, if you want to focus on accuracy, on performance, they will get you higher than a random forest can do. But you also need to be a little bit more careful for overfitting in that case, right? So hence why those techniques implement regularization and so on. So there is such a thing as overboosting. Right? With bagging-based techniques, you don't have that risk. Once you have enough trees, you can add in more, but you will just stay in the same regime. And you can try this out. I mean, if you don't believe me, make a toy data set like this in scikit-learn yourself and see what happens between a random forest and between AdaBoost. So the blue line here is the accuracy on the train data set over the number of trees. So there we know trivial to perfectly fit that. The orange line is the validation accuracy. Random forest will even out and will stay there, basically. AdaBoost, if you're boosting, It's gradual in this case because the data set is so simple, obviously, but you can see an effect that is going downwards in this case, right? So it's already a small effect of that overboosting. With more features, it will be even more pronounced, right? But as you also increase the number of trees in your ensemble, random forest will basically get stuck somewhere over here, like this is my average, and this I can't refine further from here. That's where I stick to. Whereas with boosting techniques, they will be pushed in a setting where they start fitting your training data perfectly again. So it's a trade-off, right? Hence, I do like random forests or extra trees because they are so robust. But again, if you want to have like a little bit extra accuracy or area under the curve performance, boosting is obviously the way to go. And then, and this is what leads us to our deep learning chapters, what I should also kind of as an addendum say. So for the longest amount of time, this is basically the closing chapter for tabular data. And I said, well, if you have the tabular data set, don't bother with anything else. Use one of those three, right? And that's what everybody uses, which is still the case. However, things have been changing a little bit in recent years, and especially the last 2 years. So I also wanted to highlight this a little bit. So we will talk about deep learning. So this is more already kind of an introduction to that. But generally what we saw is, well, deep learning has been kind of the champion technique whenever you move away from tabular data. From the moment you talk about text, or you talk about images, or you talk about video, you can set up simple schemes using good featureization techniques and then something like an XGBoost. But if you really want to take in the raw data and play with that, and you have a lot of that, and of course these neural networks, they tend to perform better. But with tabular data, so far, not really, because there you have a mix of numerical and categorical techniques. Your data sets might not be so large. So there we did see that those three ensemble techniques, that they form strong baselines. And so a lot of people have been wondering, well, can we come up with a way where we can utilize the things that we have been doing in deep learning and have them beat those classic three, let's say XGBoost, CatBoost, and LightGBM. And not taking deep learning and just building a standard multi-layer perceptron, as we will see, which you can do, but it won't do better than those techniques, right? So don't bother with that, but maybe even more modern inspired approaches where we use attention mechanisms and transformer-based architectures, like we do for large language models, and maybe bring some of that design to the tabular setting as well. And in most cases, well, so far, not really. CNNs, they exploit spatial properties in images, the location of pixels, and the fact that you need to learn patterns that need to apply or filters that need to apply no matter where they show up in the image. NLP, natural language processing, has a nice sequential structure in terms of text and has language and grammar that is worthwhile to exploit with more deeper, more parameterized models. Like I said, in tabular data, we are often limited to the instances that we have available. And those three ensembles, well, they give us those nonlinear interactions very easily, right? And almost, I'm not going to say for free, but very elegantly, they're very capable to learn those intricate patterns. So there have been a couple of techniques that have been proposed, techniques such as TAPNet, for instance, already for many years, in fact, and where the original paper oftentimes shows that, hey, look, we outperform XGBoost, but very quickly it was found that, well, if you do a hyperparameter sweep on your technique and you just use the defaults in XGBoost, yeah, then okay, you can win, but if you do make an honest comparison, you don't, right? And you're basically way behind what these extreme gradient boosting techniques can do. So in honest benchmarks, so far, we haven't seen a technique yet, almost, well, or not that many, that can outperform our traditional, let's say, modern tabular approaches. And like I said, with MLP, as we will see, we'll introduce MLPs, a multi-layer perceptron. That doesn't make sense. You need to normalize your numerical features again. With decision trees, you don't even have to bother. For categoricals, you're also still stuck. You need to either use embeddings there or convert them to a representation, also as we saw before. Now, you can play with that. It will give you maybe a good baseline, and even in scikit-learn, if you just want a standard MLP and you train it on the CPU, scikit-learn has an implementation for that, which you normally, I mean, building a neural network, you'd probably pick a PyTorch or a Keras to do that. So you can set that up, but then if you would compare to your gradient boosting machines, you will see that that underperforms, Either it underperforms, or it heavily overfits, or it does both. Now, there have been some tabular-specific architectures that have been proposed. So I already mentioned TabNet, that tries to take this idea of attention. There have been things such as FT Transformer, Saint, Node, Deep GBM. There have been a lot of these ideas. And it's a bit similar to what we saw in foundation models for time series, where people are playing with, well, if we first take all the data sets that are available in the world that have to do with time series, and we pre-train a model like we do with a language model on top of that, and then you can fine-tune it or utilize it on your own data set, plus we make use of some sort of attention mechanism, wouldn't that work? And in time series, we have seen that to some extent, that indeed companies such as IBM, Amazon, Salesforce, they have all been releasing foundation models for time series, which on complex settings, they do well, right? I'm not saying that for a simple time series that your ARIMA is not going to work anymore, but they are quite getting there. For tabular data, so far, even that these were promising, not really capable to outperform something like an XGBoost. Not speaking even of the times you would need to train these things and so on. So far we didn't see that very much yet. The idea makes sense. So you try to learn feature interactions explicitly. Just like in a language model, you treat the arrival of features in instances as tokens, and then you just self-attend to that, and you try to predict something from that. Like if you would give a stream of text tokens, now you give a stream of feature values, basically. So we have seen some ideas and some papers that also kind of questioned and heavily reacted to this and said, well, it concerns and ways forward. Are we really making much progress? Real faults in deep learning systems. There has been a blog post that has been keeping track of these basically tabular deep learning ideas since 2022 that basically said for all of them, well, we've had dozens of them, and people are not using them that much yet. And also transformers are what you don't need. This repo also tries to keep track a bit of that. So it would seem that the conclusion so far is, well, don't bother, you're not going to use this. You will use deep learning for images and video and audio and so on and text, but not for your standard tabular data set, which probably for the majority of cases is still true today. Except, of course, it had to happen. Like I said, this idea of a foundational model for tabular learning, there is a new kind of kid on the block, again, trained on millions of synthetic tasks, and then with a capability to be fine-tuned on new tabular data sets that you bring. And that thing is called TAP-PFM, Tabular Prior Data Fitted Network. ChatGPT, the GPT stands for Generative Pre-Training, Prior Data Fitted. It's kind of the same idea. You first learn a foundational model on lots of synthetic tasks. And you maybe come up with a couple of, well, interesting changes to the standard self-attention architecture, where you maybe do some sort of Bayesian inference and so on. The first version of this still underperformed. But miraculously enough, the company or the group behind it, Prior Labs, has been going at it. And last year, they released version 2. And just a couple of weeks ago, they released version 2.5. And for this one, already last year, I told groups for the first assignment, well, if you're in the mood, try it out, right, and see what it does. And indeed, some people did. And out of the box, we did indeed see that it gives also great results. And even more so compared to an XGBoost, which does come with a lot of hyperparameters. Random Forest does not, but XGBoost does. But also this thing comes with very little hyperparameters that you have to tune. Now, it still has some drawbacks. And one of the biggest drawbacks is that it's quite limited to the train instances that you can feed it. It works best if you have less than 10,000 instances. It does actually work on more than that as well, but you might need to tamper a little bit with it. Another drawback is that the speed of fine-tuning, of training on your exact task, that can also be quite slow compared to those more traditional approaches. Interpretability, of course, can also be an issue, but we saw that that was already an issue for those other model techniques as well. So basically, like I said, a couple of weeks ago, version 2.5 was released. some PhD researchers of mine have also been kind of experimenting with benchmarks between traditional techniques and these more tabular-inspired deep learning approaches, and have also found that actually, if I would recommend any of the tabular learners in the space of deep learning, apart from just picking XGBoost, CatBoost, or LightGBM, that this is probably the one to go for. So also this year for assignment 1, if you want to make a comparison and your computer can handle it, I would say, well, try it out, right? It's just a package that you install using pip and see what it gives you. It basically requires no hyperparameter tuning, so it's basically worth a try. Yeah? It's both for classification and regression. Yeah. Not so sure about multi-clause though, but I guess also, but that I should double check. But for sure, binary classification and regression. Yeah. Okay, so that being said, we can, I have a bit time left to introduce at least the introductory part of deep learning. Not too much, but we'll see where we get. Now that we're talking about deep learning, there's the next large part that we will tackle. And in the first chapter here, we will talk about the foundations. What is this and how does it work? Then afterwards, we will focus a bit on how we can apply this on image data, right? So we move from the tabular domain to the image domain. Later on, another part that we will move to is text. And we will see how these techniques can be applied on text. And then we'll talk also a bit about generative techniques as well. So what is there? What's the basic idea? Well, deep learning, you probably already know, well, it uses a concept called artificial neural networks. And if you talk about a neural network, that is a network of neurons, and they are artificial, so we're going to synthetically represent what a neuron does in animals or in humans by means of a mathematical function. Now, don't get too crazy about this, right? This is just a very synthetic representation of how a neural cell works in our brain. It has, other than that, very little relationship to the biology, honestly. The fact is just, well, you have cells and they can send electric signals. Well, here we will build artificial neurons that can give numerical outputs, and they can combine them with one another or send them to one another, and that's basically it. Right? In the actual human brain, there are a lot of extra things going on. We don't just have those neuron cells. There are lots of other different cells going on as well. Our brain is not just what's in our head, but it's also going down our spine. It's our visual cortex as well, let alone questions such as how we will train this thing, which is also totally not comparable between what we will use here and what actually happens in biological systems as well. So it's more like a background kind of interpretation, let's say, and a fun name, rather than there being a very heavy link there. But okay, yeah, it was inspiring at least, right? So we just came from TAP-PFN, so we already mentioned that deep learning for tabular data might not always be beneficial, but what you can say is that when your data reaches a certain complexity, like you do go to images and so on, or text, or video or audio, that this is especially the case where these networks or these techniques have found favor again. And the main reason being is that for tabular data, again, very often we're looking for some sort of representation that models can pick up on, a vector of numbers basically. If you already start with tabular data, you typically don't have too much work in terms of the representation that you need to build up. And if you do, then very often you have good manual ideas, or from your domain expertise, you can bring in features that will help that representation. Now, for other sorts of data, if I give you documents, pieces of text as instances, yeah, what's a representational vector that you can build for that, right? If I give you an image, what's a representational vector that you can build for that? And if you can do that, you can still pump that into an XGBoost or whatever, and it might be able to do a good job. But ideally, we would have something that can learn end-to-end, and from the most raw representation of data as we can feed it, can build up some internal representation automatically. In other words, it does some sort of automated feature engineering, which is very often when you hear people talk about deep learning or neural networks, they will say, well, here it's not you doing the feature engineering, there is some automated feature engineering going on instead, because you do some sort of end-to-end learning task there. Now, also important to mention is that this is itself by no means some sort of new technique. If people talk about deep learning, artificial neural networks, they have been around for a very long time. And even the notion of, hey, it would be nice that we can stack layers of these neurons on top of each other in order to make the networks deeper, also had been known about for a very long time. Right? It's not that this was rediscovered, right? What was the case, however, in the early days of this is that, well, it didn't work. First of all, the compute availability was not there. Right? There was, okay, you can design these things, but if you don't have a way to train them, it won't work. Second, the size of data sets at disposal back then, also not large enough. So that's another aspect that triggered the current revival. Coding this thing up to train such deeper networks, basically manually going through the derivations. Today, there is software that basically helps you with that, where you can just define your architecture going from left to right, and it figures out how it should do all the back propagation, how it should implement the optimization. So also less manual work there. There are some other aspects as well that we'll see, but basically this was discovered already long before, but at that time simply didn't work. And that's a bit where this history comes from, and you will see, I mean, we can go even further than the 1960s. It already started in the first kind of neuron design already in the 1940s, where the threshold logic unit, as this thing was called, where you, and again, it all is based on, as we will see, the same idea. You have some input signals coming in a single synthetic neuron, and that single synthetic neuron produces some sort of output. And it's associated with a couple of weights. And in the first examples, well, you can play with the weights, but we have no way to learn them. And then next up, well, we have a way to learn the weights for a single neuron, but now we want to link multiple neurons to each other. A single neuron, that's not even a fruit fly. You might have seen the example where I think its EON system has been able to completely simulate the brain of a fruit fly and is having the thing fly around in a simulated environment. There is also a company called Cortical Labs who are using real human neural cells. You can buy those and you can put them in a chip and are using that thing to play Doom. So that's a demonstration that they showed. So you need to go further than a single neuron. So what you can do is you can take a couple of them, you can implement them in parallel next to each other, and then you can play with that, and then you can be like Rosenblatt at the time, who presents this thing and who talks with the New York Times and says, well, now we almost have thinking machines, you know. Now we are very close to machines that will feel emotions, that will think, and they will perhaps even reproduce, right? So he was very good at marketing, but didn't really happen, right? Because very quickly after that, Marvin Minsky, together with some colleagues, basically showed that, well, everything that you have so far, this whole neat system of kind of synthetically representing neurons, it is even incapable to learn and to train to solve a very simplistic class of problems. What since then has been discussed or has been noted, the XOR problem, the exclusive OR problem, but where they basically showed, well, nice theory and so on, but you still have some sort of a linear model going on there, right? And you have no way around that. Well, they did know a way around that, but they said, well, instead of just putting neurons in parallel, we need a real network, right? It's called an artificial neural network for a reason, so we need at least stacks of these things. But then they didn't know how to train them, how to make the weights or the parameters of such a setup learnable. And people said, well, forget about it. Right? We give up. Right? This will never work. The theory is not there, which led to the first AI winter, a long period where people gave up on the idea of using neural networks. Until Geoffrey Hinton, with again a couple of friends, say, well, we have found a way to train them. We can use a concept called backpropagation. Basically, the chain rule when you calculate derivatives, but applied in a stepwise manner. And it's not perfect, but at least there is a way to train these things now. Okay, let's try them out on computer vision problems and so on. But then we ran into the issues where people found out, well, if we want to make these things deeper, they are way too expensive to train. We need to wait a long time. We need a lot of data examples. And what we also notice is due to the way how we train these things, the more deeper that we make them, well, either they have a very heavy tendency to overfit, and we don't know how to deal with that, or they train very slowly. and we also don't know how to solve them. And meanwhile, from Russia, there was a couple of researchers visiting the US, Bell Labs, and they brought with them the concept of support vector machines. And they showed, well, we see that you guys are trying to use neural networks for some simple digit detection and computer vision. Well, here is a different approach, and let's compare both of them. And it turned out that at that time, the support vector machine approach worked way better. It was tractable to compute. It was theoretically way more worked out, whereas neural networks have always been some sort of empirical throw stuff at the wall and see what sticks mentality. So people said again at that time, well, let's give up on this idea of neural networks, even though we know that we can make them large and we can train them. It's just impractical if we want to do that. There is this other thing which is way more theoretically neat, and people gave up again. And that, again, that is then called the second AI winter, and that stayed until the 2010s, more or less, where we saw the introduction of AlexNet, a computer vision-based neural network again, which played in a competition called ImageNet. And ImageNet is basically a whole bunch of images with 1,000 classes that you need to predict. And that was going along at a slow-paced scale, and yeah, no one was outperforming what humans could do. And models were using manual feature engineering and things in OpenCV and filters and so on. But okay, suddenly that neural network enters the competition and smashes everybody that came before that, manages to cut the error rate in half based on everything that came before. And that made people awake and say, whoa, where does this come from? And neural networks are back at the front stage. And since then, thanks to the usage of GPUs and thanks to having more data sets and thanks to figuring out ways to make these deeper stacks of networks trainable again, up until today, this has been still with us. After that followed the arrival of LLMs, large language models, and AI and generative AI. And even though some people are either claiming that there is a bubble, which financially there might be, but maybe also there is a bubble in terms of, well, at some point this will collapse or people will lose interest. Other people are claiming, well, we're close to reaching AGI, artificial general intelligence, where you can take some sort of model and have it been or have it applied in all sorts of settings. Maybe we're also not quite there yet, but I think it's fair to say that this whole usage of these type of techniques, they're with us and they're there to stay, right? So at least that we need to admit. And also interesting is that already in the 80s, when people were trying to play around with like smallish neural networks, that already you see concepts such as, this is an article from '89, for instance. This is, you could call this one of the first self-driving cars, or self-driving truck in this case, with a very limited camera attached in the front. Pixels, maybe 100 by 100 pixels, black and white images. And actions that the car can take is basically left, right, forward, backwards. But already at that time, people were asking, well, how do we make this thing a bit more interpretable? How can we uncover what these weights are doing, what's in those hidden layers, and so on? So you see that very much there are still the same questions that are being asked nowadays in terms of interpretability and so on, and trustworthiness of those models as were being asked back then. So like I said, in 2010, we had that ImageNet challenge. So in the first years, top models had an error rate of 25%. And then came along AlexNet in 2012, where they entered the competition with, again, a deep learning-based approach. Again, Ilya Sutskever, Alex Krizhevsky, and Jeffrey Hinton, and they halved the error rate. And they combine a couple of things that have since become a mainstay. So they decide, hey, well, we have these GPUs now. Can't we utilize this to train these neural networks on? Rather than doing on the CPU, GPUs are good at matrix multiplications on a massive parallel scale. Let's try that. We want something that's deeper. We know that has issues in terms of training. Well, maybe there is a way how we can make that a little bit more stable, such as playing around with that activation function that people have been using and replacing that with something that has since then been known as the ReLU, the rectified linear unit activation function, which we'll see is very simple, but helps to mitigate some issues when you want to train deeper networks. This thing has a tendency to overfit, so maybe we can do something against that. So they also introduce a method called dropout to mitigate that as well. And so it's the combination of these Yeah, small improvements, you could say, but brilliant ideas on their own. And suddenly you have a model that is doing better than everything else that came before that. And since then has been, well, cited, it's already more than 120,000 times by now. So many people consider this as kind of the start or the startup or the deep learning kind of starting phase in 2012. And since then, yeah, we have seen other types of architectures, from convolutional neural networks to recurrent neural networks to transformer-based architectures. We have gotten better software to both design those kind of models and train them, like TensorFlow, PyTorch, Keras, many others, new optimizers and so on. And what we do see today in the space of AI, and it's still the case today, coming from the background of people in the second AI winter, kind of giving up on this empirical idea and believing that there should always be a grounded theory, like was the case with SVMs, is that now this field is again completely back to empirical approaches. A lot of experiments, a lot of practice, a lot of seeing what works. Still if you look at what the AI labs today are doing to design language models and designing new types of attention mechanisms and designing new types of mixture of expert mechanisms, it's very empirical. It's experimentation, and maybe something works and maybe something doesn't. I'm not saying that's the best way to do it, but that's the reality that we see ourselves in today. So like I said, general AI, not quite here yet, GAI or AGI, whatever you want to call it. This prediction of this third AI winter, probably unlikely. Although there will always be some issues to be tackled. I mean, we know that in terms of ethical concerns, for instance, especially today with what OpenAI is doing, but also before, hallucination of models, maybe some models driving people to do things that they shouldn't do and so on, interpretability, that there are still some challenges also in this space left to solve. But okay. Software, a lot. Yeah, so I will already mention, I think if you will have to make a choice on the right-hand side, these are the most popular ones nowadays. PyTorch tends to be the most utilized package nowadays in research settings. It's very much loved. Also in industry, it took a while, but it has been adopted more and more. So I would say that's the standard. But as a starter, it can tend to be a little bit verbose, a little bit messy to work with, so might not be the easiest. So that's why some people still prefer to utilize Keras to get started with. Has a lot of tutorials for simple cases, also works quite well. So you can check that out and try to learn a bit from that. TensorFlow, that's Google's library. In industry, used to be a little bit more loved because it had a very good production story. Deploying models on a smartphone or on different devices is something that they supported quite well. But yeah, the people at Google, they can't help themselves. Whilst they're already working on version 2 of TensorFlow, they will tell you, well, don't use version 2 because it's not ready yet, and don't use version 1 because it's out of date. And meanwhile, they're already working at some new thing. So JAX is another one that comes from the Google team that some people have switched to, but hasn't been that widely adopted. And then there is also for the people who like to use the Julia programming language, there you have things such as Flux. As a researcher starter, I would say either pick PyTorch or Keras. It's quite likely that if you would work in industry that you might be dealing with TensorFlow as well. Now, it doesn't really matter which one you use because they all offer kind of the same thing anyway. They will give you a mechanism to design your architecture. They will implement a bunch of optimizers to optimize the weights on training data, implementing backpropagation and automatic differentiation, and then basically some utility tools around that, as we will see. Now, what is the basic idea then? We can start by at least introducing our one neuron, let's say. On this slide, so we'll introduce one neuron and we will introduce the original perceptron, a type of neuron. Later we'll see others, but this is your basic building block, let's say. So one neuron, we will also often call this one unit in the synthetic brain that we want to build. So if you hear people talking in architecture about the units, they mean the same thing as neurons here. Every neuron or every unit in these networks that we will design generally all work in a very similar way. They take in input signals, very often coming from other neurons before them, and they combine those input signals to produce some sort of output. And that output we will also call the activation of the neuron. In this case, the activations that we will look at, but that will change a bit later on, but at least for now, the activation of a neuron will be a single scalar, a single number. And in early designs, that was something either -1, 1, or 0. For us, it's just a floating point number. So we already can define a couple of, or one type of neurons in the network that we built, input neurons. We need to start from somewhere. If I have an instance with 3 features, x1, x2, x3, I need to provide those signals to the rest of the network that I will build here. So these 3 neurons, they're just there as data feeders, basically, right? They don't calculate anything on their own. They don't have weights that they need to learn, but they do have an output. The output or the activation simply depends on the instance that I'm feeding in. So maybe x1 is age, so then for the first instance, this neuron says 33 as its output, and for the next instance, 35, and so on. The triangle that you see here, that's then the actual neuron that does the work, let's say, in my single working neuron-brained animal that I'm building here. And that's the perceptron, so that's a triangle. And it says, well, take in those outputs that you got, the activations that you got from the input neurons, so x1, x2, x3, and basically what you do is multiply each of them with a weight and sum that together. So it's a linear combination, right, of the inputs that you receive. And the weights here, well, those are the parameters. Those are the things that in the case of a perceptron, in the beginning we set them to something random, but those are the things that we will learn based on data. What's the output of this perceptron? Well, the result of this calculation. Again, a single number, right? Sum of products in this case. But we can go a step further later on if we would like to add in non-linearities and stuff like that. Well, don't just take a sum of products like this, but also take that result and squeeze it through some sort of function. And let's call that an activation function. And whatever that is, well, you pick. You're the designer of this thing, right? Maybe something that looks like a hyperbolic tangent or whatever, or just linear, right? And you don't do anything with the result, you just keep it as is, right? But just you can transform the result as a final step with that activation function. You can split out these 2 steps if you want, right? Or you can put them in the same kind of unit architecturally, whatever, same thing. And yeah, now that we're at it, maybe we can also add in some sort of bias weight as well. In logistic regression or in your linear regression, you would have called this the intercept, right? And that's just something where the input unit just gives a constant value of 1. So it's 1 that gets multiplied with this bias weight, which I can also learn. So then if I say, hey, for this f here, let me pick a sigmoid, what do I get? Well, if I want to get the output of an input matrix or instance, I take the sigmoid of the sum of the weights times the values plus the intercept, or the bias, as we tend to call it in deep learning. We don't like to use intercept, so the bias. Well, that looks very familiar, right? That's the exact same as logistic regression was, right? So the question here then, well, how do we determine the weights? And with logistic regression, we said, if your matrix is full rank, then there is a closed form formula, given that you use this loss that you want to optimize, and you have ordinary least squares, right? You can set those weights in one go. Yeah, but not here, right? Because later on, we will use different loss functions. I will make this network way more complex, so we can't get those weights in one go. We need to optimize them iteratively using some algorithm, step by step, by going multiple times through our training data. And that algorithm is called gradient descent. Aha! I already spoke about gradients when I spoke about XGBoost, so here it comes again. And gradient descent basically says, well, all those weights that you have, the next time you want to update them, set them equal to the previous value for that weight minus some lambda times the first partial derivative of your loss function with respect to that weight. Basically, what this is saying is if you have two weights, let's say, so I look top down, loss goes out of the blackboard, and we have a contour landscape, maybe something like this, and I start with my weights over here, find the gradient, find the direction that goes steepest downwards, and move in that direction. First partial derivative, so I do not really know the step that I should take. That's what the lambda is. The lambda is the learning rate. And it says, well, at least based on the steepness, multiply that with your lambda, multiply this gradient with your lambda, and then you get how far of a step you want to take. If you set it very small, every iteration you will take a small step, so you will need to do a lot of training. It's robust at least, but you might also end up in a local minimum. If you set it very high, you might bounce around, right? So there is only one in gradient descent hyperparameter that you need to set, and it's a crucial one, is this lambda, is that learning rate. Whatever you will do in deep learning, that learning rate will again come back to bite you. With different optimizers, they're a little bit less sensitive to you setting a good learning rate value, luckily. There have been people trying to work on optimization schemes that do not need a learning rate or can do that automatically, but it is still a fundamental one in there because we only use that first partial derivative. In tutorials, the formula at the top of the slide is the correct one. When you would look at, okay, I want to implement this now in Python, see if this works. This simple perceptron that I have here, let me implement stochastic gradient descent with sigmoid and with the sum of squared errors as my loss function, or mean squared error. And then you might find, well, how do I calculate the first partial derivative? I don't want to work that out myself. And then you will maybe find a tutorial that says, you know, in your for loop, every weight that you have, the new weight is going to be the old one plus the learning rate times your expected value minus the predicted value times the input associated to that weight. And let's say we're trying to do binary classification. Why is that? Well, let's say I use a sum of squared errors. So squared errors is my loss. And I have two weights, so I have two features plus a bias weight. Well, we can calculate the first partial derivative, right? So here I use a shorthand. I say, well, O is just this thing right before I squeeze it through this sigmoid function. So W1 times X1 plus W2 times X2 plus the bias weight. And I know that gradient descent tells me that I need to calculate the loss in accordance or the partial derivative with respect to the individual weights. Well, I know what my loss is, right? That is basically my true value minus my predicted value squared. So I need to calculate that in accordance with this weight. I can then use a chain rule to split it up a bit, bring the square to the front. I still have this to work out. I can bring the -1 to the front here, so then I only have this one to work out. And the predicted value, I kind of know what that is as well, right? I know that that is that output that the network gives me, squeezed through a sigmoid. That sigma here stands for the sigmoid function, and squeezed through there. I again can use the chain rule, and then I can look up on Wikipedia, okay, what is the first derivative of the sigmoid function? Well, it's this thing, right? So here in blue is the sigmoid function, as you know it from before. The orange line is the first derivative there. So, I can at least look that up. I can plug that in. Now I only have this to work out, and I know, well, the first partial derivative of this output thing with regards to a specific weight, right? Well, if the weight is 1, then it's x1. If the weight is 2, then it's x2. If the weight is the bias weight, then it's just 1, right? So I know that it's equal to xi, x1, x2, or just 1 in the case of the bias weight. So then I have my fully worked out first partial derivative. I know my solution. And then I can simplify that a bit, and I can say, well, everything which is well, this 2 here, that's just a constant. So basically, I can throw that out. If I take a look at how large that first partial derivative gets, it's not a constant, but it's close. It's between 0 and about 0.22, right? So I can also just consider that to be the same thing no matter where I am, right? So basically, I can throw out a lot of parts out of this, right? And I can only bring in the important pieces, and the important pieces are expected minus predicted, xi, and I still have this minus here. So that's why if this thing contains a minus, minus times minus, that's why it becomes a plus here. And all those other constants, I say, well, I don't need to keep them in there. I can just change my learning rate, or I can have my learning rate work on a different scale. Before it was 8, now it has to be 16, whatever, right? I just take that as a constant. The only things I need to calculate is this part. And if you implement this, then indeed you will see that your weights converge. But only in the case where you have a simple perceptron, and only in the case where you use squared errors as your loss, right? If you have more, and this already reveals why this was so cumbersome in the 80s, if you have to go over this first partial derivative and do that for all the 8 billion weights that you have, you won't do that, right? So that's not what we do. So hence, automatic differentiation will allow us that we can construct our network from left to right, and that it works out automatically the differentiation steps that it needs to apply. So that's a big help, of course, for us. But what we're doing is the same thing what I have just shown. We are looking at our loss, we are in a certain position, and we're basically checking what's the direction that all of my weights have to move in. And the learning rate determines the size of my steps, the speed of the convergence. But too high is not good because then I will bounce around. Too low is not good because I will need more iterations of training and I might get stuck in that local minimum. So that will actually be the crucial hyperparameter that I need to set. And again, on these curves, it's just a single weight. But imagine that this is a landscape where you have an 8 billion dimensionality, but same thing. In that 8 billion dimensional space, I'm closing my eyes and looking at the direction that I should move all of them in. And that's basically it. Where does the loss come from? Well, expected minus predicted, right? Loss will always come from comparing the output that my network gives me thus far to what are my actual labels. Right? In the case of binary classification, my expected is a 0 or a 1, and my predicted is a probability at the end of my network. Like the case of my sigmoid here, again, I get something between 0 and 1. That also means that every time I want to move my weights, I need a loss, so I can move my weights based on one training example. Or what I could do is I could take all my training examples, calculate a loss for all of them, average that loss, and move the weights based on that. But what is the case is that I won't be able to get in the optimal position of my weights after just doing one pass of my training data. So typically I need to do that a couple of rounds, right? And those rounds are called epochs of training. So an epoch is a full pass over your training data. And when that's done, you shuffle your data to increase the stability a bit, and you do it again. And every time you're checking, compare the output of my network with the expected, calculate some sort of loss, MSE, cross entropy, whatever you want, and based on that loss, figure out the steepness, move the weights. And no matter you have 2 weights, 5 weights, 8 billion weights, that will be the same optimization behind that. So that doesn't change no matter the size of the network that you're working with, which sounds a bit strange that this scales from something that looks like logistic regression to something that will have way more weights in practice, but it is the exact same thing. And that's thanks to GPUs that can do this on such a massive scale, right? Hence the improvements in compute that we have nowadays. So here you see the same kind of loss function, but with 2 weights, and you see that stochastic gradient descent tries to find its way by changing the weight step by step until it finds some optimal position. So we minimize a function by following the gradients of the cost function. So we need to be able to take the first partial derivative of this loss. Not everywhere, it doesn't need to be fully convex, and we will see that sometimes we use activation functions that are not differentiable everywhere, because they involve some sort of absolute value, for instance. But that's okay, right? It doesn't need to be differentiable everywhere. As long as it's relatively smooth, we can find the right direction, right? If you would come up with some sort of crazy loss landscape, which is all over the place or completely flat, then this would cease to work, obviously, right? But we can take some leeways in terms of how differentiable that this thing needs to be, okay? Okay, and just maybe as an, something to check out before we end for today.
Only 2 minutes recording time remaining.
Thank you. This is AI helping me. Yeah, this site is extremely slow always, so I will try to, yeah. There have been people that have tried, well, a loss landscape where you don't have just 2 weights, but you have 8 billion weights. Can you still apply some form of dimensionality reduction to still show it as a 3-dimensional landscape? And what you indeed see, this is what a loss landscape, for instance, looks like if you reduce it to 2 dimensions. So stochastic gradient descent does have a lot of challenges, even in fact, to kind of move its way to one of those minimal points, right? But it does work, as you can see. Okay, so yeah, I will also stop, but hence systematic is the same, and next week we will then continue with this story.